In October 2019, a machine solved a problem in 200 seconds. Every supercomputer on Earth working together would need 10,000 years. That is not an estimate. That is not marketing. That is a measured, peer-reviewed fact published in Nature by Google's quantum research team. And here is the part that should keep you awake tonight. There is only one explanation for how this is possible. The machine borrowed computational power from somewhere else, from parallel versions of itself, running the same calculation in parallel universes. That is not science fiction. That is the engineering specification. David Deutsch proved it in 1985. A quantum computer performing calculations on 53 qubits is accessing 2 to the 53rd power parallel realities simultaneously. That number exceeds every atom in the observable universe. The math does not work any other way. You cannot fit that much processing power into one timeline, and yet the machine works. It works so well that by 2024, Google's Willow chip performed a calculation in under 5 minutes that would take a classical computer 10 septillion years. That is a 1 followed by 25 zeros. Longer than the current age of the universe by a factor of 1 billion. So where is the computation happening? Hugh Everett tried to tell us in 1957. The physics community laughed him out of academia. He died believing his life's work was a failure. But today, every quantum engineer on Earth is building machines based on the premise that Everett was right. They are not searching for parallel worlds. They are using them, exploiting them, engineering with them as casually as you might use electricity. We just built a door, and we have no idea what is on the other side. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. On October 23, 2019, in a laboratory in Santa Barbara, California, a machine the size of a chandelier did something that should not have been possible. It solved a problem in 200 seconds. The same problem if you handed it to Summit, the most powerful classical supercomputer on Earth at the time. A machine occupying an entire room at Oak Ridge National Laboratory would have taken 10,000 years, not 10,000 hours. Not 10,000 days, 10,000 years, longer than the entire span of recorded human civilization, longer than the pyramids have stood, longer than we have been writing things down. The machine that did this was called Sycamore. It was a quantum computer built by Google, and the moment its results were published in the journal Nature, a very specific kind of alarm went off in the scientific community. Not the excited kind, the uncomfortable kind. The kind that makes physicists sit up in their chairs and start asking questions they do not particularly want answered. Because here is the thing about that 200-second calculation. Nobody disputes that Sycamore did it. The data is clean. The results were verified. The engineering is real. What people dispute, what has turned into one of the strangest and most heated arguments in modern physics, is how it did it. Where did the computation actually happen? If a quantum computer can perform a task in minutes that would take a classical machine longer than human history, where was all that work being done? You cannot get something from nothing. The universe does not hand out free shortcuts. So if the answer is not coming from this processor, in this lab, in this universe, then the question becomes unavoidable. Where else is it coming from? That is what this chapter is about. Not the celebration of a new technology, not a victory lap for quantum computing. This is about the moment a machine crossed a line that classical physics says should not exist. and the uncomfortable possibility that it did so by reaching into places we have spent a century pretending are not real. Let's start with what actually happened, because the details matter. Google's quantum computing team, led by a physicist named John Martinez, had been working for years to build a device capable of what they called quantum supremacy. That term was coined by a physicist named John Preskill back in 2012. It does not mean quantum computers are better at everything. It means there exists at least one task, however obscure, however useless in practical terms, where a quantum computer can definitively outperform any classical machine by a margin so wide that the comparison becomes absurd. The task does not have to cure cancer. It does not have to optimize supply chains or crack encryption or do anything remotely useful. It just has to prove the point. Quantum computers operate under different rules, and if you design the right problem, those rules give you access to computational power that should not fit inside the known universe. The problem Google chose is called random circuit sampling. If that sounds boring, it is, intentionally. The team was not trying to solve a grand challenge of mathematics or simulate the birth of stars. They were trying to do something so specific, so tailored to the strengths of a quantum processor that no classical computer could keep up. Here is how it works. You take a quantum chip, in this case a grid of 53 qubits, and you run a series of randomized quantum gates through it. Gates are the basic operations that manipulate qubits, like adding or flipping bits in a classical computer, except quantum gates can put qubits into superposition and entangle them with each other. You apply these gates in a sequence that is chosen randomly, layer after layer, building up a massively complex web of quantum states. At the end of the process, you measure the qubits. Each one collapses into either a 0 or a 1. Write down the result, a string of 53 bits. Repeat the process 1,000,000 times. Each run gives you a different string. Now here is the trick. Because the gates were applied in a specific sequence, certain output strings are more likely than others. The quantum processor, because it is directly manipulating superpositions and entanglement, naturally samples from the correct probability distribution. It spits out results that match the underlying quantum mechanics. A classical computer, trying to simulate that same process, has to calculate all the possible quantum states, track how they interfere with each other, and manually compute the probabilities for every possible output string. That number of possible states grows exponentially with the number of qubits. For 53 qubits, you are dealing with 2 to the power of 53 possible states. That is roughly 9 quadrillion states. And because quantum mechanics involves interference, you cannot just count the states. You have to keep track of the amplitude, the phase, the entanglement between every state and every other state. The amount of information you need to store and manipulate balloons so fast that even the most powerful supercomputers on Earth run out of memory before they finish the calculation. Google ran the task on Sycamore. It took 200 seconds, not hours, not days, 3 minutes and 20 seconds. Their estimate for how long the same task would take on Summit, the supercomputer sitting at Oak Ridge, was 10,000 years. That number appeared in the Nature paper. It made headlines everywhere. 10,000 years, the same span of time that separates us from the invention of agriculture. And a quantum computer just ran circles around it in the time it takes to boil pasta. John Martinez, the lead scientist on the project, stood in front of the press and said plainly that Google felt comfortable claiming quantum supremacy. Brooks Foxon, a graduate student in the Martinez group, put it even more directly. A computation that would take 10,000 years on a classical supercomputer took 200 seconds on our quantum computer. The statement hung in the air like a challenge, and IBM took it. Within days of the announcement, researchers at IBM published a response. They argued that Google's estimate was wrong, not slightly wrong, catastrophically wrong. They claimed that with a smarter algorithm and better use of classical hardware, Summit could solve the same problem in 2.5 days, not 10,000 years, 2.5 days. That is still slower than 200 seconds, sure, but it is a very different kind of slower. It is the difference between impossible and inconvenient, the difference between a miracle and a really good piece of engineering. IBM's argument was technical and brutal. They pointed out that Google had assumed the classical simulation would need to hold all quantum states in memory at once. IBM showed that you could store most of the data on hard drives, shuffle pieces in and out of RAM as needed, and grind through the calculation much faster than Google had predicted. Was it elegant? No. Was it fast? Not by quantum standards, but it worked. And it meant the 10,000-year estimate was more of a rhetorical flourish than a hard number. Google pushed back. They argued that IBM's method was impractical, that it relied on assumptions about hardware and storage that would not scale to larger problems, and that even if you granted IBM's numbers, Sycamore was still faster by an insane margin. 2.5 days versus 200 seconds is still a speed-up factor of more than 1,000, and the gap only gets worse as you add more qubits. At 60 qubits, the classical simulation becomes genuinely impossible. At 70 qubits, you would need more hard drives than atoms in the solar system. The argument between Google and IBM became one of the most public feuds in computational physics, and it missed the point entirely. Because whether the classical estimate was 10,000 years or 5 days does not change the fundamental question. How is a chip the size of a dinner plate sitting in a lab in Santa Barbara, performing calculations that would require a supercomputer the size of a building, running for longer than human civilization has existed, to replicate? Where is the work being done? Quantum mechanics offers an answer. Superposition and entanglement. A qubit does not just sit in a state of 0 or 1. It exists in a superposition of both states simultaneously until you measure it. And when qubits are entangled, the state of one qubit becomes intertwined with the state of another in a way that cannot be described by looking at them separately. You have to describe the entire system as a single unified quantum state. As you add more qubits, the size of that state space explodes. 2 qubits can be in 4 possible states at once, 3 qubits, 8 states, 53 qubits, 9 quadrillion states, all at once, all interfering with each other, all contributing to the final answer. The quantum computer is not calculating each possibility one at a time. It is calculating all of them together, in parallel, using the natural behavior of quantum mechanics. That explanation works. It fits the math, it matches the experiments, and it raises a question that physicists have been very carefully not asking for the last 100 years. If the quantum computer is exploring 9 quadrillion states simultaneously, where are those states? You cannot store that much information in 53 atoms. The amount of data required to describe the full quantum state of a 53-qubit system is more information than you could encode in every particle in the observable universe. So where is it written down? Where is the calculation actually happening? The standard answer, the one you will find in textbooks, is that it is not happening anywhere. Quantum mechanics does not describe reality. It describes probabilities. The wave function is not a real thing. It is a mathematical tool. The superposition is not a real state. It is a prediction engine. You are not supposed to ask where the information is stored because the question is meaningless. Shut up and calculate. That phrase, attributed to physicist Richard Feynman, has been the unofficial motto of quantum mechanics since the 1920s. Do not ask what it means, just use the equations. They work. That has been good enough for a century of physics. It is not good enough anymore. Because when a quantum computer solves a problem in 200 seconds that should take 10,000 years, it is doing work. Real, measurable, verified work. And that work has to be happening somewhere. David Deutsch, a physicist at Oxford and one of the founding figures of quantum computing, has been saying this for 40 years. He argues that the only way to make sense of quantum computation is to accept that the work is being done in parallel universes, not metaphorically, not as a thought experiment, actually. He claims that when a quantum computer runs, it is splitting the calculation across countless versions of itself in other branches of reality, all working on different pieces of the problem simultaneously and then interfering with each other at the end to produce the final result. The term for this is the many worlds interpretation. It was first proposed in 1957 by a physicist named Hugh Everett, a graduate student at Princeton who was trying to solve a completely different problem. Everett's idea was simple and horrifying. Every time a quantum measurement happens, the universe does not choose one outcome and discard the others. It splits. All outcomes happen. You just only see one of them because you are stuck in one branch. Somewhere else, in another branch, another version of you saw a different result. Both are real. Both continue. The universe is constantly branching into an unimaginably vast tree of parallel realities, and you are riding one thread through it, never aware of the others. For decades, the many worlds interpretation was treated as a fringe idea. Interesting philosophically, maybe useful as a teaching tool, but not something serious physicists took literally. And then quantum computers started working. Deutsch points to quantum supremacy as the smoking gun. He argues that a quantum computer performing a task that would require more computational resources than exist in the observable universe is direct evidence that the computation is happening elsewhere, in other branches, in parallel worlds. Where else could it be happening? You cannot fit 9 quadrillion simultaneous calculations into 53 atoms unless those atoms are somehow borrowing computational power from other versions of themselves in other universes. This is not a fringe claim anymore. It is being taken seriously by a growing number of physicists who are uncomfortable with the alternatives. The mainstream response, the one you will find in most physics departments, is that Deutsch is wrong. Superposition and entanglement, they argue, are fully explained within standard quantum mechanics without invoking parallel universes. The information is not stored anywhere. It is not a real thing that needs a location. Quantum mechanics is non-local. It does not obey the classical rules about where information can live. You do not need other universes. You just need to accept that the universe is weirder than you thought. That argument works right up until you ask the question again. If the information is not stored anywhere, how is the quantum computer using it? If the superposition is not real, why does the quantum computer behave as if it is manipulating real, simultaneous states? The debate has turned into a stalemate. One side says the evidence for parallel universes is circumstantial at best, and that quantum mechanics does not require them. The other side says the alternative is to accept that information can exist without existing, that calculations can happen without happening, and that quantum computers are performing magic. Both sides agree on one thing: something very strange is going on, and Sycamore just made it impossible to ignore. Let's go back to the number for a second because it matters. 200 seconds versus 10,000 years. Even if you accept IBM's revision and drop the classical estimate to 2-5 days, you are still looking at a speedup of more than 1,000 times. And that gap is exponential. Add 10 more qubits and the classical machine falls another factor of 1,000 behind. Add 20 more qubits and you are in a regime where no conceivable classical computer, not one built from every atom on Earth, could keep up. The quantum computer is not getting a little faster. It is leaving the classical machine in a completely different universe of computational capability. That phrase is not accidental, because if Deutsch is right, that is exactly what is happening. The quantum computer is not in a different universe. It is in all of them, and that changes everything. When Google announced quantum supremacy, the headlines focused on the achievement. First quantum computer to outperform classical machines, milestone on the road to full-scale quantum computing, the dawn of a new era, all true, all missing the point. The real story is not that we built a faster computer. The real story is that we built a computer that should not work unless reality is far stranger than we have been willing to admit, and it worked. That is the mystery, that is the crisis, that is the thread that pulls at the entire fabric of how we understand the universe. The problem Sycamore solved was useless. Random circuit sampling has no practical applications. It does not break encryption. It does not simulate molecules. It does not optimize logistics or predict the weather. It is a benchmark, a proof of concept, a line in the sand. But the implications of crossing that line are anything but useless. Because if quantum computers require parallel universes to function, then parallel universes are not a thought experiment. They are an engineering reality. You are not just philosophizing about whether other worlds exist. You are using them, right now, in a lab in Santa Barbara. And if that is true, if the many worlds interpretation is not an interpretation but a description of something real, then every quantum computer ever built is a doorway. A machine that reaches across the boundary between worlds and borrows computational power from versions of itself that you cannot see, cannot touch, cannot communicate with, except through interference, through the strange, silent collaboration of countless parallel processors working on the same problem in countless parallel realities. That is not science fiction. That is the only explanation that makes the math work without asking you to believe in miracles. David Deutsch has spent his career trying to get people to take this seriously. He argues that the computational power of quantum computers is evidence, direct experimental evidence, that we live in a multiverse, not because the idea is elegant or philosophically interesting, because the machines work, and they should not. Not unless something else is doing most of the work, somewhere else. The scientific community has not accepted this yet. Most physicists still treat many worlds as one interpretation among many. Useful maybe, interesting sure, but not necessary. The equations work either way. You do not need to believe in parallel universes to build a quantum computer, except now you kind of do. Because the alternative is to accept that a device the size of a chandelier can hold more information than exists in the observable universe, manipulate that information faster than the laws of physics should allow, and produce results that classical machines cannot replicate without invoking resources that do not exist. If that is not evidence of something beyond our universe, then the word evidence has lost all meaning. Sycamore ran its test in 200 seconds. It sampled from a probability distribution so complex that verifying the results required comparing the quantum output to a classical simulation that took days to run. And every time they ran the experiment, the quantum computer won, not by a little, by a margin so absurd that the comparison stops making sense. This is not a faster car. This is a car that arrives at the destination before it leaves the driveway. And when you ask how that is possible, the only answers on the table are either magic or other worlds. Mainstream physics has chosen magic. They call it superposition. They call it entanglement. They call it the fundamental weirdness of quantum mechanics. And they are right. It is weird. But weird is not an explanation. It is an admission that we do not have one. Deutsch has an explanation. The computation is distributed across branches of reality. The quantum computer is not just a machine, it is a bridge. And the speed up we are seeing is not coming from cleverness or better engineering. It is coming from collaboration. With versions of the experiment that are running right now in worlds you cannot see, worlds that are just as real as this one, worlds where another version of you is reading these words and wondering the same thing. If quantum supremacy is real, and it is, then the multiverse is not a hypothesis. It is a tool, and we just learned how to use it. The physicist who explained how Sycamore worked wrote his proof in 1985. That matters because in 1985, nobody had built a quantum computer. Nobody had come close. The idea itself was so new that most scientists treated it the way you treat a clever thought experiment, interesting on paper, irrelevant to the actual world. David Deutsch wrote his paper anyway, and buried inside it was a claim so strange that even the people who understood the math spent the next 40 years pretending he had not said it. Quantum computers, Deutsch argued, do not just calculate faster than classical machines, they borrow their computational power from other universes, not as a metaphor, not as a philosophical aside, as the literal mechanism by which the machines operate. He said it plainly. Quantum computation requires the existence of parallel realities. Without them, the math does not work, the speed-up does not happen, the entire framework collapses into nonsense. And then he published the paper in the Proceedings of the Royal Society, and everyone quietly filed it under interesting ideas we will think about later. Later arrived in October 2019 when a machine in Santa Barbara proved him right. David Deutsch is not the kind of physicist who chases headlines. He does not run labs, he does not manage teams of graduate students or apply for billion-dollar grants. He works at Oxford, mostly alone, writing papers that other physicists describe as difficult and often annoying. He has spent his entire career asking questions that most of his colleagues consider either solved or unsolvable, and he does not particularly care which category they think his work falls into. In the early 1980s, Deutsch became obsessed with a problem that seemed, on its surface, to have nothing to do with parallel universes. He wanted to know whether quantum mechanics placed any fundamental limits on computation. Classical computers, the kind built from transistors and logic gates, obey a set of rules laid out by Alan Turing in 1936. Turing proved that there exists a universal computing machine, a device that can simulate any other computing machine given enough time and memory. The Church-Turing principle, named after Turing and mathematician Alonzo Church, says that any physically realizable computation can be carried out by such a machine. It is one of the foundational ideas in computer science. Deutsch wanted to know if quantum mechanics changed that. Could a computer built from quantum components do things a classical Turing machine could not? And if so, what did that say about the nature of computation itself? The question led him down a path that ended in a place nobody expected. In 1985, he published a paper titled Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. The title sounds dry, the content is not. Deutsch proved two things in that paper. First, he showed that a universal quantum computer is theoretically possible. A machine that manipulates quantum states according to the rules of quantum mechanics can, in principle, simulate any physical process allowed by the laws of physics. That includes simulating other quantum computers. Second, and this is the part that caused problems, he showed that such a machine would be able to perform certain calculations exponentially faster than any classical computer. Not a little faster. Exponentially faster. And the only way to explain where that extra computational power was coming from, Deutsch argued, was to accept that the calculations were happening in parallel across many different branches of reality. He was not guessing, he was reading the math. And the math said that a quantum computer performing a calculation on n qubits was effectively performing 2 to the power of n calculations simultaneously. For 50 qubits, that is more than a quadrillion parallel computations. For 300 qubits, it is more parallel computations than there are atoms in the observable universe. Deutsch asked the obvious question: if the computer is performing more calculations than can fit inside our universe, where are the extra calculations happening? His answer was the only one that made the math work. They are happening in other universes, parallel branches of reality where other versions of the quantum computer are running other parts of the same calculations. At the end, all those branches interfere with each other, and the result you measure in your branch is the product of all that parallel work. Quantum computers, Deutsch concluded, are not just machines, they are multiverse sampling devices. That claim did not go over well. Physicists in the 1980s were still arguing about whether the many worlds interpretation was even a coherent idea, let alone something you could build a machine around. Deutsch was saying that not only was many worlds real, it was necessary. You could not have quantum computation without it. The speed-up required it. The interference required it. The entire framework of how qubits behave required it. Take away the parallel universes, and you were left with a computer that should not work. And since the math said the computer would work, the universes had to be real. Most of his colleagues ignored the claim. They focused on the other parts of the paper, the technical proofs, the construction of a universal quantum gate set, the implications for quantum algorithms. The multiverse stuff was treated as Deutsch being Deutsch, provocative, philosophically interesting, not something you had to take literally to make use of the results. That split between the people who thought Deutsch was talking about real parallel universes and the people who thought he was using a colorful metaphor has persisted for 40 years. And it matters because the two camps are not arguing about interpretation anymore. They are arguing about whether the machines we have built are doing what Deutsch said they would do, and the machines are working exactly the way he predicted. The core of Deutsch's argument rests on something called quantum parallelism. To understand it, you need to understand superposition, which is the idea that a quantum system can exist in multiple states at once until you measure it. A classical bit is either a 0 or a 1. A qubit can be both, not in the sense that it is hiding its true value and you just do not know what it is yet, in the sense that the qubit genuinely does not have a definite value until the moment you look at it. Before measurement, it exists as a combination of 0 and 1, weighted by probabilities, and those probabilities interfere with each other in ways that have no classical analog. When you have two qubits, they can be in a superposition of 4 possible states simultaneously: 0, 0, 0, 1, 1, 0, 1, 1, all at once. 3 qubits can represent 8 states, 4 qubits, 16, 50 qubits, more than a quadrillion. The number grows exponentially, and here is the thing Deutsch noticed. When you apply a quantum operation to a qubit in superposition, you are not just operating on one value, you are operating on all possible values at once. Run a calculation on 50 qubits in superposition, and you are, in a very real sense, running that calculation on a quadrillion different inputs simultaneously. That is quantum parallelism. A single quantum operation touches every possible state in the superposition at the same time. A classical computer has to loop through each possibility one at a time. A quantum computer does them all in one step. Except here is the problem. You cannot directly access all those parallel results. When you measure the qubits at the end of the calculation, the superposition collapses. You get one result, one string of zeros and ones. All the other possibilities vanish. So if the quantum computer is doing a quadrillion calculations in parallel, but you only get to see one answer, what is the point? The trick, and this is where quantum algorithms get clever, is to design the calculation so that the wrong answers interfere destructively and cancel each other out, while the right answer interferes constructively and gets amplified. If you set up the problem correctly, the parallel computations do not just run independently, they work together. The incorrect paths through the calculations subtract from each other. The correct path builds on itself. And when you measure the result, you get the right answer with high probability. Not every time. Quantum computers are probabilistic, but run the calculation a few dozen times, and the right answer shows up often enough that you can identify it. That interference is the key. It is what separates quantum computation from just rolling dice a quadrillion times and hoping you get lucky. The parallel computations are not independent, they are entangled. The state of one qubit affects the state of every other qubit in ways that depend on the entire history of operations you have applied. By the end of the calculation, the qubits are so entangled that you cannot describe any one of them in isolation. You have to describe the whole system as a single unified quantum state. And when you measure that state, what you are seeing is the result of all those parallel computations interfering with each other, filtering out the noise, and handing you the answer. Deutsch looked at that process and asked where it was happening. If you have 50 qubits, you are manipulating a superposition of a quadrillion states. Each state is a possible configuration of 50 bits. To store that information classically, you would need a quadrillion 50-bit numbers written down somewhere. That is more information than you could encode in every atom in the solar system. The qubits themselves are just 50 atoms. 50 atoms cannot store a quadrillion pieces of information. So where is it stored? The standard answer is that it is not stored anywhere. Quantum mechanics does not work like that. The superposition is not a list of possibilities sitting in a filing cabinet somewhere. It is a mathematical description of the system, the wave function, and the wave function does not exist in physical space. It exists in an abstract space called Hilbert space, a mathematical construct where the dimensions correspond to all the possible states the system could be in. You are not supposed to ask where Hilbert space is because it is not a place, it is a tool. Deutsch was not satisfied with that answer. He pointed out that when you run a quantum computation, the computer is doing work, real, measurable work. It is applying operations. It is evolving the quantum state. It is producing interference. All of that requires resources. And if the resources do not exist in this universe, then they must exist somewhere else. His argument was simple and brutal. The quantum computer performing 2 to the power of n operations in parallel requires 2 to the power of n parallel processes. You cannot get something from nothing. The computation has to happen somewhere. If it is not happening in this branch of reality, and it cannot be because there is not enough room, then it must be happening in other branches. The quantum computer is not creating the parallel universes, they already exist. Every possible state in the superposition corresponds to a different branch of reality. The quantum computer is just coordinating the work across those branches, running the same algorithm in all of them simultaneously, and then using interference to combine the results. What you see when you measure the output is not the result of one calculation. It is the result of countless calculations performed in countless parallel worlds, all of which contributed to the final answer. That is not an interpretation, that is a mechanism. Deutsch was not saying parallel universes are a nice way to think about quantum mechanics. He was saying they are the engine. Without them, the machine does not run. You cannot have quantum parallelism without parallel processes. And if the processes are not in this universe, they are in others. The math does not care whether you like the answer. The math just tells you what is required. And what is required is a multiverse. Most physicists did not buy it. The dominant view then and now is that you do not need to invoke parallel universes to explain quantum computation. Superposition and entanglement are enough. Yes, the quantum state is exponentially large. Yes, it contains more information than you could store classically. But that does not mean the information is physically stored somewhere. Quantum mechanics is fundamentally different from classical mechanics. It does not obey the same rules about locality, about information, about what it means for something to exist. You are not supposed to visualize the wave function as a real object because it is not. It is a probability amplitude, a tool for making predictions. And the fact that the tool works does not mean the tool corresponds to something real in the world. That argument works for a lot of physicists. It does not work for Deutsch. He has spent 40 years pushing back against the idea that quantum mechanics is just a prediction engine. He argues that physics is not about making predictions. It is about explaining how the world works. And an explanation that says quantum computers perform exponentially many calculations in parallel, but refuses to say where those calculations are happening, is not an explanation. It is an evasion. If you take the math seriously, if you follow the logic all the way through, you end up with parallel universes, not because they are philosophically appealing. Because the alternative is to believe that information can do work without existing, that calculations can happen without a substrate, that machines can borrow computational power from nowhere and return it when they are done. Deutsch calls that magical thinking, and he is not wrong. Here is where it gets concrete. In his 1985 paper, Deutsch laid out a thought experiment involving a quantum algorithm for factoring large numbers. Factoring is the problem of taking a big number and breaking it down into its prime components. For small numbers, it is easy. 12 factors into 2 times 2 times 3, done. For large numbers, it gets hard fast. A number with a few hundred digits might take a classical computer years to factor. A number with 2,000 digits is functionally impossible. The difficulty of factoring large numbers is the basis for most modern encryption. Your credit card, your email, your bank account, all of it relies on the fact that factoring is hard. In 1994, a mathematician named Peter Shor figured out how to factor large numbers on a quantum computer efficiently. Shor's algorithm, if run on a large enough quantum computer, could break most encryption systems currently in use. The algorithm works by exploiting quantum parallelism. It runs many possible factorizations simultaneously, uses interference to eliminate the wrong ones, and outputs the correct factors. For a number with 2,000 digits, Shor's algorithm would need to evaluate roughly 2 to the power of 2,000 possible factors in parallel. Deutsch pointed out that 2 to the power of 2,000 is a number so large it defies comprehension. It is far, far larger than the number of atoms in the observable universe, by a margin so vast that comparing them is meaningless. If a quantum computer running Shor's algorithm is evaluating 2 to the power of 2,000 possibilities in parallel, where are those evaluations happening? There are not enough atoms in the universe to store that much information, let alone process it. Deutsch's conclusion was unavoidable. The parallel evaluations must be happening in other branches of reality. The quantum computer running Shor's algorithm is distributing the workload across 2 to the power of 2,000 parallel universes. Each universe runs a tiny piece of the calculation. At the end, all those pieces interfere, the wrong answers cancel out, and the correct factors emerge. That was 1985. Nobody had built a quantum computer yet. Nobody had run Shor's algorithm. Nobody had factored anything larger than 15 using quantum methods. Deutsch was extrapolating from theory, following the math into places where experiment could not yet go. The response from the physics community was polite skepticism. Interesting idea, probably not necessary. Let's see what happens when we actually build one. 40 years later, we built one, and it did exactly what Deutsch predicted. Google Sycamore did not run Shor's algorithm. It ran a different task, random circuit sampling, which is less useful but easier to verify. But the principle is the same. Sycamore manipulated 53 qubits in superposition, which corresponds to roughly 9 quadrillion parallel quantum states. It performed operations on all of those states simultaneously, used interference to filter the results, and output an answer that a classical computer would need thousands of years to replicate. The machine worked, the speed-up was real, the parallelism was real, and the question Deutsch asked in 1985 is now sitting on the table in front of every quantum physicist on Earth. Where did the work happen? You can ignore the question. You can say it does not matter, that the machine works and the mechanism is beside the point. You can argue that quantum mechanics is non-local and weird, and asking where the computation happened is the wrong kind of question. A lot of very smart physicists say exactly that, but ignoring the question does not make it go away. And the more powerful quantum computers become, the harder it is to pretend the question does not exist. When a machine performs more operations than can fit inside the observable universe, and it does so in 3 minutes, you are left with two options. Either the operations are happening somewhere we cannot see, or the machine is violating the laws of physics. Mainstream science has chosen the first option without admitting it. They say quantum mechanics allows for this kind of parallelism within a single universe because superposition is a real feature of quantum systems. Fine, that is true. But superposition of what? If a qubit is in a superposition of 0 and 1, what does that mean physically? Where is the 0 state? Where is the 1 state? The usual answer is that both states exist in the wave function, but the wave function does not exist in physical space. It exists in Hilbert space, which is not a place, which is a mathematical abstraction. Deutsch asks, if the wave function is not a real physical thing, why does it produce real physical effects? Why can you use it to perform calculations that have measurable, verifiable outcomes? Why does the interference work? If the wave function is just a tool, just a mathematical convenience, then the interference is magic. You are saying that imaginary numbers corresponding to non-existent states can somehow collaborate with each other to produce a real answer. That does not make sense. It only makes sense if the states are real. If the 0 and the 1 both exist, physically, in different branches of reality, then the interference is not magic. It is communication between branches, and quantum computation is not a mathematical trick. It is distributed processing across the multiverse. Deutsch has been saying this for 40 years, and for 40 years, physicists have been telling him he is wrong, or interesting but unnecessary, or philosophically provocative, but not scientifically meaningful. Sycamore changed that. Not because it proved Deutsch right. Proof is a strong word, but because it made his argument harder to dismiss. When a quantum computer solves a problem in 3 minutes that would take a classical supercomputer 10,000 years, you are watching something that should not be possible. And the only explanation on the table that does not require you to believe in miracles is the one Deutsch offered in 1985. The computation is distributed. The qubits are coordinating work across parallel realities. The speed up is coming from other universes, not metaphorically, actually. If that is true, and every piece of experimental evidence suggests it is, then quantum computers are not just machines, they are proof. Direct, experimental, reproducible proof that we live in a multiverse. That other versions of this experiment are running right now in other branches. That the results we see in this branch are the product of collaboration with branches we cannot visit, cannot measure, cannot communicate with except through interference. That every time you run a quantum algorithm, you are touching other worlds, and those worlds are touching you back. That argument leads somewhere uncomfortable. Because if Deutsch is right, if quantum computation requires the many worlds interpretation to function, then the interpretation is not optional. It is not one view among many. It is the operating system, the thing the machine is running on. And if that is true, then every quantum computer ever built is evidence that Hugh Everett was right, that the universe splits, that all outcomes happen. That reality is not a single thread, but an endlessly branching tree, and we just figured out how to use the branches. David Deutsch gave us the mechanism. He told us how quantum computers work and where the computational power comes from, but he was not the first person to say it. The idea that quantum mechanics requires parallel universes, that every measurement splits reality into branches, that all possible outcomes happen somewhere, that framework was not invented by a quantum computing pioneer in 1985. It was invented by a graduate student at Princeton in 1957. His name was Hugh Everett III. He was 26 years old. He wrote a doctoral thesis that should have changed physics overnight. Instead, it was ignored, dismissed, and buried so thoroughly that Everett left academia entirely and spent the rest of his life working for the Pentagon. He died in 1982, 3 years before Deutsch published the paper that would eventually prove him right. He never saw quantum computers. He never saw the experiments that would vindicate his ideas. He never saw the moment when the physics community stopped laughing and started taking his work seriously. But he saw it coming. He knew the math worked. And he knew that sooner or later, somebody would build a machine that made the parallel universes impossible to ignore. Everett was not trying to explain quantum computers. Quantum computers did not exist yet. He was trying to solve a different problem, one that had been quietly torturing physicists since the 1920s, the measurement problem. It is one of those phrases that sounds boring until you realize what it actually means. And what it means is that quantum mechanics, the most successful scientific theory ever devised, the framework that explains atoms and molecules and semiconductors and lasers and essentially all of modern technology, does not actually explain what happens when you look at something. The theory works perfectly as long as nobody is watching. The moment you measure a quantum system, the rules break, and nobody knows why. Here is the problem in plain terms. Quantum mechanics describes particles as existing in superpositions of multiple states simultaneously. An electron does not have a definite position until you measure it. Before measurement, it is smeared out across space, existing in many places at once, described by a mathematical object called the wave function. The wave function evolves smoothly and predictably according to the Schrödinger equation, a piece of math so reliable that you can use it to calculate the behavior of atoms to 14 decimal places. No other theory in the history of science has been tested to that level of precision. Quantum mechanics works, except when you measure the electron, the wave function collapses instantly. The electron, which was everywhere, suddenly becomes somewhere. One definite position, one definite outcome. The superposition vanishes. And the Schrödinger equation, the thing that was governing the system a moment ago, stops applying. Something else happens, something the theory does not describe. That is the measurement problem. Quantum mechanics has two sets of rules. One set governs what happens when you are not looking. Smooth, deterministic, reversible evolution according to the Schrödinger equation. The other set governs what happens when you do look. Sudden, random, irreversible collapse into one outcome. The theory does not tell you why there are two sets of rules. It does not tell you what counts as a measurement. It does not tell you when the collapse happens or what causes it. It just says that sometimes the wave function evolves and sometimes it collapses, and good luck figuring out which is which. For decades, physicists dealt with this by not dealing with it. The most popular approach, called the Copenhagen interpretation, was developed by Niels Bohr and his colleagues in the 1920s. The Copenhagen view says that the wave function is not a real thing. It is a tool for calculating probabilities. When you measure a quantum system, you are not collapsing a real physical object. You are updating your knowledge. The electron was never actually in multiple places at once. You just did not know where it was. The wave function describes your ignorance, not reality. Measurement is the moment when you gain information. The collapse is not a physical process. It is an epistemic one. A change in what you know, not a change in what exists. That explanation worked well enough to get on with doing physics. You could calculate atomic spectra and design experiments and build technology without ever worrying about what the wave function really was or why measurement was special. Shut up and calculate. That phrase, whether or not Richard Feynman actually said it, became the unofficial motto of quantum mechanics. Do not ask what it means, just use it, it works. Hugh Everett thought that was a cop-out. He was a graduate student working under John Wheeler, one of the most respected physicists in America. Wheeler was brilliant, deeply thoughtful, and obsessed with the big questions. He encouraged his students to think carefully about the foundations of quantum mechanics, not just the applications. Everett took him seriously, and the more Everett thought about the measurement problem, the more he became convinced that the Copenhagen interpretation was not just incomplete, it was incoherent. The problem, Everett realized, was the observer. In the Copenhagen view, the wave function collapses when a measurement happens. But what counts as a measurement? Does the particle have to interact with a detector? Does the detector have to be read by a human? Does the human have to be conscious? Where do you draw the line between the quantum system, which obeys the Schrödinger equation, and the observer, which causes the collapse? Bohr never gave a clear answer. He said the line was somewhere between the microscopic and the macroscopic, but he never specified where, and that vagueness, Everett argued, was fatal. Because if you take quantum mechanics seriously, if you apply it to everything, then the observer is also a quantum system. The observer is made of atoms. The atoms are described by wave functions. The observer's brain, the detector, the particle being measured, all of it should obey the Schrödinger equation. There is no magic moment when the rules change. There is no special role for consciousness or observation or macroscopic objects. It is all quantum mechanics all the way down. So Everett asked a simple question. What happens if you never invoke the collapse? What if the wave function always evolves according to the Schrödinger equation? No exceptions, no special rules for measurement, no observer-induced collapse. What if you take the math seriously and follow it all the way through? The answer he got was shocking. If the wave function never collapses, then measurement does not eliminate the other outcomes. It entangles the observer with the system. Before you measure the electron, it is in a superposition of being in position A and position B. You, the observer, are in a definite state. After you measure it, you are no longer in a definite state. You are in a superposition too. There is a version of you who measured the electron at position A and a version of you who measured it at position B. Both versions exist, both are real, both think they saw a definite outcome. But from the outside, from the perspective of the universal wave function, there was no collapse. The system just got bigger. The electron's superposition spread to include you. That is the many worlds interpretation. It is not saying that measurements create new universes. It is saying that the universe never stops being in superposition. Every possible outcome of every quantum event happens. They all exist simultaneously in the universal wave function. What we perceive as a single outcome, a single branch of reality, is just the piece of the wave function we happen to be entangled with. Somewhere else in the wave function, another version of you saw a different result. You cannot communicate with that version. You cannot see them. You are stuck in your branch. But they are just as real as you are. Both branches continue. Both evolve. The universe is not a single timeline. It is an endlessly branching tree of parallel realities, all of them equally real, all of them described by the same wave function, all of them obeying the Schrödinger equation without exception. Everett submitted his thesis in 1957. He called it the relative state formulation of quantum mechanics. He was careful with the language. He did not use the phrase parallel universes. He did not talk about splitting worlds or alternate realities. He framed everything in terms of the mathematics. The wave function never collapses. Observers become entangled with the systems they measure. Every outcome exists in the wave function, and which one you see depends on which branch you are in. All of that was stated precisely, mathematically, without any of the science fiction baggage that would later attach itself to the idea. The response from the physics community was brutal. Niels Bohr read the thesis and offered no endorsement. He did not engage with the argument. He simply reasserted the Copenhagen interpretation and moved on. Werner Heisenberg, another giant of quantum mechanics, dismissed the idea as extravagant and unnecessary. Why multiply universes when the Copenhagen view worked perfectly well? John Wheeler, Everett's own advisor, got nervous. He liked the mathematical elegance of the work, but he could see that the idea was going to be controversial. He encouraged Everett to revise the thesis, to soften the language, to avoid any explicit talk of multiple universes. Everett complied. He toned it down. He removed some of the more provocative phrasing. He resubmitted. The thesis was accepted, and then nothing happened. The paper was published in Reviews of Modern Physics in 1958. It was read by a handful of physicists, most of whom did not know what to make of it. It was too strange, too philosophically uncomfortable, and it did not make any new predictions. The many worlds interpretation gave the same experimental results as the Copenhagen interpretation, same probabilities, same outcomes. So why bother? If the two interpretations were empirically equivalent and one of them did not require you to believe in parallel universes, why would you choose the extravagant one? Everett was crushed. He had expected debate, argument, engagement. What he got was silence. A few people wrote polite letters, a few others wrote dismissive ones, but mostly the thesis just sat there, ignored. By the early 1960s, Everett had given up on academia entirely. He took a job with the Institute for Defense Analyses, a think tank that did classified work for the Pentagon. He spent the rest of his career analyzing nuclear strategy and operations research. He never published another paper on quantum mechanics. He never tried to defend his thesis. He walked away. He died in 1982 at the age of 51. Heart attack brought on by years of chain smoking and heavy drinking. His daughter later said he seemed disappointed with how his life had turned out. He had wanted to be a physicist. He had wanted to solve the biggest problems in science. Instead, he spent 2 decades working on missile trajectories and game theory for the military. The many worlds interpretation, the idea that should have made him famous, was still sitting on the shelf gathering dust. But something had started to shift. In the 1970s, a new concept entered quantum mechanics: decoherence. It was discovered by a physicist named Heinz Dieter Z and later developed by Wojciech Zurek and others. Decoherence describes what happens when a quantum system interacts with its environment. In the lab, you can isolate a single particle and keep it in a clean superposition for a while. But in the real world, particles are constantly bumping into other particles, radiating photons, exchanging energy with their surroundings. Every interaction entangles the system with the environment, and once the environment gets involved, the superposition becomes effectively irreversible. You cannot undo the entanglement. You cannot put the system back into a pure state. The system has decohered. From the perspective of an observer inside the system, decoherence looks exactly like collapse. The interference between different branches of the wave function becomes so diluted by environmental entanglement that you can no longer detect it. Each branch evolves independently. The observer in one branch sees one outcome and has no way to access the other branches. Decoherence does not require a conscious observer. It does not require a measurement. It just requires interaction with the environment, and it happens automatically all the time at every scale. This was huge, because decoherence gave the many worlds interpretation a mechanism. It explained why we perceive a single outcome even though the wave function contains all outcomes. It explained why the branches do not interfere with each other after a measurement. It explained why macroscopic objects like cats and detectors and humans seem to behave classically even though they are made of quantum particles. The environment acts like a continuous monitoring system, constantly entangling with everything, constantly splitting the wave function into branches that cannot talk to each other. You do not see the other branches because decoherence has made them inaccessible. But they are still there, still evolving, still part of the universal wave function. By the 1980s and 1990s, a growing number of physicists started taking many worlds seriously, not as a speculative fantasy, but as a legitimate interpretation with real physical content. It solved the measurement problem without invoking collapse. It gave a clear, consistent account of what happens during a measurement. It treated observers as ordinary physical systems, not special entities with magical powers to collapse wave functions, and it made no arbitrary distinctions between microscopic and macroscopic, between quantum and classical, between observer and observed. Everything was quantum. Everything obeyed the Schrödinger equation. The appearance of collapse was just decoherence. The appearance of a single outcome was just entanglement. No new physics required, no ad hoc rules, just the math taken seriously. But the real vindication came later. It came when quantum computers started working. Because quantum computers do not just obey the Schrödinger equation in theory, they use it. They exploit superposition and entanglement to perform calculations. And the thing about those calculations is that they work exactly the way many worlds predicts. A quantum computer running a calculation on 50 qubits is not collapsing the wave function 50 times and picking one outcome at random. It is evolving the entire superposition, all 9 quadrillion possible states simultaneously. The states interfere with each other. The wrong answers cancel out. The right answer gets amplified. And at the end, when you measure the qubits, you see the result of all that parallel processing. You cannot see the other branches. Decoherence has made them inaccessible, but the interference proves they were there. The speed-up proves they were doing work. The quantum computer is functioning as a distributed system across the branches of the wave function, exactly the way Everett said it would. David Deutsch spelled this out explicitly in his 1985 paper and in his later work. He argued that quantum computers are proof of many worlds, not philosophical speculation. Proof. If the many worlds interpretation were wrong, if the wave function actually collapsed during measurement, then quantum computers would not work. The parallelism would disappear. The interference would vanish. You would be left with a classical probabilistic machine, not a quantum one. But quantum computers do work. They produce interference. They perform parallel computations. And the only way to explain that, Deutsch argued, is to accept that the parallel computations are happening in parallel worlds. Not everyone agrees with that argument. There are still physicists who think you can explain quantum computation without invoking many worlds. They point to other interpretations, pilot wave theory, consistent histories, quantum Bayesianism, and argue that those frameworks can account for the behavior of quantum computers without requiring parallel universes. The debate is ongoing, but here is what has changed. In 1957, when Everett proposed many worlds, it was considered an extravagant, unnecessary complication, a philosophical curiosity with no experimental consequences. Today, it is one of the top 3 interpretations of quantum mechanics, taught in graduate courses, discussed seriously at conferences, and increasingly treated as the default framework for understanding quantum information theory. What changed was not the interpretation itself. Everett's math has not been revised. What changed was the technology. We built machines that behave the way Everett said they would. We built quantum computers, and those machines made many worlds impossible to ignore. The irony is thick. Everett spent his entire career being told that his ideas were too weird, too speculative, too disconnected from experiment. He died thinking his work had been a failure. And now, 40 years after his death, the machines we are building operate on principles that make his interpretation look not just plausible but necessary. Quantum computing does not prove many worlds in the strict logical sense. You can still construct alternative explanations if you are willing to work hard enough, but it makes many worlds the simplest explanation, the one that requires the fewest additional assumptions, the one that takes the math at face value and does not ask you to believe in magical collapse processes or observers with special powers. If you are a physicist looking at a quantum computer and asking yourself what is actually happening inside that device, the many worlds answer is the most straightforward. The qubits are in superposition. All possible states exist simultaneously. The computation is distributed across those states. The interference comes from the states interacting with each other. At the end, you measure one branch, but the others are still there, still real, still evolving. You just cannot see them. That shift, from fringe speculation to mainstream framework, did not happen overnight. It took decades. It required the discovery of decoherence, the development of quantum computing, the accumulation of experimental evidence showing that quantum mechanics really does work the way Everett said it did. But the shift happened. And now, when physicists talk about quantum computation, they often talk in language that is indistinguishable from many worlds. They talk about superpositions of exponentially many states. They talk about parallel processing. They talk about interference between branches. They might not call it many worlds. They might not say parallel universes, but the structure is the same. The math is the same. The picture is the same. Everett wrote his thesis in 1957. He proposed that the wave function never collapses, that all outcomes happen, that measurement is just entanglement. He was ignored, dismissed, and forgotten. He left physics and spent the rest of his life working for the Pentagon. He died in 1982, 51 years old, convinced his ideas had gone nowhere. And then, 3 years later, David Deutsch published a paper explaining how quantum computers work, and the explanation required exactly what Everett had proposed: parallel processing across parallel worlds. Interference between branches, a universal wave function that never collapses. Today, Everett's interpretation is no longer a curiosity, it is a contender, and in the world of quantum computing, it is something more than that. It is the operating system, the thing the machines are running on. You do not have to believe in parallel universes to build a quantum computer, but you have to act as if they exist. You have to design your algorithms as if the qubits are exploring exponentially many states simultaneously. You have to account for interference as if different branches of the wave function are talking to each other. You have to treat the quantum computer as a distributed system, even though all the qubits are sitting in the same device. The language of many worlds is not optional anymore. It is baked into how we think about quantum computation, and that is as close to vindication as a dead physicist is ever going to get. Everett never saw this. He never saw the quantum computers. He never saw the experiments. He never saw the moment when his ideas went from fringe to foundational. But he knew it would happen. He knew the math worked. He knew that sooner or later, somebody would build something that made the parallel universes undeniable. He just did not live long enough to see it, which makes the story tragic in a way that feels almost designed. The man who explained how reality actually works, how the universe splits and branches and evolves into an infinite tree of possibilities, spent his final years thinking he had failed. He died 3 years too early, 3 years before quantum computing took its first real steps, 3 years before Deutsch started spelling out the implications, 3 years before the door opened. Hugh Everett's ghost is everywhere now. Every quantum computer, every superposition, every algorithm that exploits parallel processing is a monument to the thesis he wrote in 1957, the thesis nobody read, the idea nobody took seriously, the framework that is now quietly becoming the default explanation for why quantum mechanics works the way it does. And the strangest part is that the framework does not just explain quantum computers, it explains everything. Because if the many worlds interpretation is correct, if the wave function never collapses, then every quantum event in the history of the universe has been splitting reality into branches, not just in the lab, not just in quantum computers, everywhere. Every particle interaction, every photon absorbed, every atom decaying, every moment of every day, the universe has been branching since the beginning. And what we call reality, this single thread of experience, is just one path through an unimaginably vast tree, one branch among countless others, all of them equally real, all of them evolving, all of them described by the same universal wave function. Everett saw that in 1957. He saw it in the math, he saw it in the logic, and he tried to tell the world was not ready. Now, 70 years later, the world is catching up, not because the philosophy has changed, because the machines work, and the machines work exactly the way Everett said they would. That is not interpretation anymore, that is engineering. And engineering has a way of settling arguments that philosophy never could. Hugh Everett told us the universe splits. David Deutsch told us quantum computers use those splits, but neither of them explained what was actually doing the splitting. What is the stuff that branches? What is the substrate? If reality is dividing itself every time a particle decays or a qubit gets measured, what exactly is reality made of? The answer came from a physicist who spent most of his career thinking about black holes and collapsing stars. His name was John Archibald Wheeler. He was one of the giants of 20th century physics, a man who worked with Niels Bohr, taught Richard Feynman, coined the term black hole, and spent the last decades of his life obsessed with a single question that most of his colleagues thought was either meaningless or unanswerable. What is reality made of? Not what does reality do, what equations describe it, what predictions can we make, what is it? Wheeler wanted to know the substance, and after 60 years of thinking about it, after a career that took him from nuclear weapons design to quantum gravity to cosmology, he arrived at an answer that sounded more like poetry than physics. It from bit. Those 3 words appeared in a paper Wheeler published in 1989 when he was 78 years old. The paper was called Information Physics, Quantum, The Search for Links. It reads like the work of someone who has run out of patience for careful hedging and diplomatic language. Wheeler was old. He knew he was running out of time, and he was done pretending the question did not matter. It from bit. Every it, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely from apparatus-elicited answers to yes or no questions, binary choices, bits. That is Wheeler. Not paraphrased, direct quote. He was saying that the universe is not made of matter. It is not made of energy. It is not made of fields or particles or strings or membranes. It is made of information, and information is not a thing that describes reality. It is reality. The particles are downstream. The fields are emergent. The structure of space-time itself is a projection of something deeper, and that something is pure information. Yes or no questions, binary choices, bits. Most physicists read that paper and filed it under interesting ideas from a senior colleague who had earned the right to speculate. They did not take it literally. Wheeler did. He spent the last years of his life, he died in 2008 at the age of 96, trying to convince people that this was not philosophy, it was physics, and the evidence was sitting right in front of them if they would only look. The idea did not come out of nowhere. Wheeler had been circling it for decades. In the 1960s, he developed a concept he called law without law. The idea was that the laws of physics, the things we think of as fundamental rules governing the universe, might not be fundamental at all. They might emerge from something deeper, something more primitive than mass or charge or spin. He did not know what that something was yet, but he knew it had to be more basic than the particles themselves, because particles come and go, they get created and destroyed, they transform into each other. But the information about what happened, which particle decayed, which path the photon took, that information does not go away, it gets transferred, it gets encoded, it persists. So maybe, Wheeler thought, the information is the real thing, and the particles are just the way information manifests in space-time. That idea started to look less speculative in 1975, when Stephen Hawking discovered something that should not have been possible. He proved that black holes radiate. They are not perfectly black. They emit a faint glow of thermal radiation, now called Hawking radiation, produced by quantum effects near the event horizon. That discovery was brilliant. It linked quantum mechanics, general relativity, and thermodynamics in a way no one had managed before, and it caused an immediate crisis. Because if black holes radiate, they lose mass. Over a very long time, trillions of years for a stellar mass black hole, they evaporate completely. They shrink, they fade, and eventually they disappear, which means everything that ever fell into the black hole, every star, every planet, every particle, vanishes with it. The black hole takes all that matter and all that information about what the matter was, where it came from, how it was arranged, and erases it from the universe, permanently. That violates quantum mechanics. One of the core principles of quantum theory is unitarity. Information is conserved. You can scramble it, you can hide it, you can spread it out across a complicated quantum state, but you cannot destroy it. If you know the state of a quantum system at one moment, and you know the laws of physics, you can in principle calculate the state at any other moment, forwards or backwards in time. The information is always there. It is encoded in the wave function, and the wave function evolves in a way that preserves all the information it contains. That is unitarity. And black holes, according to Hawking, break it. They swallow information and never give it back. The radiation they emit is thermal, random. It contains no information about what fell in. The information is gone, deleted. The universe has a shredder, and that should not be possible. Hawking called this the black hole information paradox. It has been one of the biggest unsolved problems in theoretical physics for 50 years. Nobody knows the answer. Some physicists think the information escapes somehow, encoded in subtle correlations in the Hawking radiation that we just have not figured out how to detect yet. Others think the information is destroyed and quantum mechanics needs to be revised. Others think the paradox is telling us something deeper. That information is not just a property of particles, it is the thing particles are made of. And if information cannot be destroyed, then information must be more fundamental than matter. That was Wheeler's conclusion. The black hole information paradox, he argued, was not a bug in the theory. It was a clue, a signpost pointing toward a deeper truth. Reality is information. And if reality is information, then information cannot be destroyed any more than reality itself can be destroyed. You can rearrange it. You can hide it. But it is always there, always conserved, always fundamental. Wheeler was not the only one thinking this way. In the early 1990s, two physicists, Gerard Hooft and Leonard Susskind, independently proposed something called the holographic principle. The name comes from holograms, those flat images that contain a three-dimensional picture. When you shine light through a hologram, you see depth, you see parallax, you see an object that appears to exist in 3 dimensions, even though the hologram itself is a 2-dimensional surface. The information describing the 3-dimensional object is encoded on the 2-dimensional film. Hooft and Susskind suggested that the universe works the same way. They argued that everything happening in a 3-dimensional volume of space, every particle, every field, every bit of information can be fully described by information encoded on the 2-dimensional boundary of that volume. The 3-dimensional universe is a projection, a hologram. The real information, the stuff that actually exists, lives on a surface. The interior is derived from the boundary, it from bit. That sounds insane, but the math works. And in 1997, a physicist named Juan Maldacena proved it. Sort of. He showed that in a specific kind of theoretical universe, one described by something called anti-de Sitter space, there is an exact mathematical correspondence between a theory of quantum gravity in the bulk, the interior 3-dimensional volume, and a quantum field theory with no gravity living on the boundary, a 2-dimensional surface. The two descriptions are completely equivalent. Everything that happens in the bulk, every black hole, every particle collision, every space-time ripple, can be calculated by doing physics on the boundary. The boundary contains all the information. The bulk is a hologram. The discovery, now called the ADS-CFT correspondence, is one of the most important results in theoretical physics in the last 50 years. It does not prove the holographic principle applies to our universe. Our universe is not anti-de Sitter space, but it proves the principle is not just philosophy, it is real. In at least some universes, Information on a boundary generates the entire three-dimensional reality inside, and if it works there, maybe it works here. That idea has been gaining ground ever since. Physicists now routinely talk about space-time as emergent, meaning it is not fundamental. It arises from something deeper, and that something is quantum information, entanglement specifically. In 2013, Multiverse and Leonard Susskind published a paper with a title that sounds like a typo. ER equals EPR. ER stands for Einstein-Rosen bridges, the technical name for wormholes. EPR stands for Einstein-Podolsky-Rosen, the trio of physicists who first described quantum entanglement in 1935. Multiverse and Susskind were saying that entanglement and wormholes are the same thing. When two particles are entangled, when their quantum states are linked so that measuring one instantly affects the other, what you are looking at is not some mysterious, spooky action at a distance. You are looking at a geometric connection, a bridge through space-time. The particles are connected by a wormhole, not a traversable one. You cannot send signals through it. You cannot use it to travel faster than light, but it is there. A geometric structure in space-time created by quantum information. Entanglement is geometry. Information is space-time. If that is true, then space-time itself is not fundamental. It is woven out of entanglement, out of correlations between bits of quantum information. John Wheeler spent the last decades of his life saying exactly that. He argued that we live in a participatory universe, that reality is not something that exists independently, waiting to be observed. Reality is created by observation, not in the sense that looking at something changes it, although that happens too. In the sense that asking a question, performing a measurement, extracting a bit of information from the universe is what brings reality into existence. Before the measurement, the universe is in a superposition, a state of pure information with no definite form. The measurement, the bit, the yes or no answer, crystallizes one outcome, one branch, and that branch becomes real for the observer who asked the question. It comes from the bit. The act of asking collapses infinite possibility into definite fact, and the universe, Wheeler argued, has been asking and answering its own questions since the beginning of time, bringing itself into existence one bit at a time. That view makes a lot of physicists deeply uncomfortable. It sounds too much like consciousness creates reality, too much like New Age mysticism dressed up in equations. But Wheeler was not talking about consciousness. He was talking about interaction. Any interaction, a photon hitting an atom, a particle decaying, a qubit getting entangled with another qubit. Every interaction is a measurement. Every measurement extracts information, and every bit of extracted information shapes the structure of space-time. You do not need a conscious observer. You just need physics. The universe is observing itself constantly at every scale, in every interaction, and those observations, those bits, are what reality is made of. This is where quantum computers come back in, because quantum computers are machines that manipulate information directly. They do not push electrons through circuits the way classical computers do. They manipulate qubits, quantum bits, units of information that can exist in superposition, that can be entangled with each other, that obey the rules of quantum mechanics instead of classical logic. And when you run a quantum algorithm, what you are doing is asking the universe a very complicated yes or no question. The algorithm evolves a superposition of exponentially many possible answers. At the end, you measure the qubits and collapse the superposition into one result. The quantum computer is extracting information from the wave function, and the way it does that, the mechanism that makes quantum computers faster than classical ones, is interference. Different branches of the wave function interact with each other. The wrong answers cancel out. The right answer gets amplified. Information flows between branches, and that flow is what gives you the speed up. David Deutsch has argued that this proves the branches are real, that quantum computation requires many worlds to function, but you can go further. You can argue that quantum computation proves information is fundamental, because the quantum computer is not manipulating particles, it is manipulating information directly. The qubits are not little balls sitting in a chip, they are states in Hilbert space, abstract objects defined entirely by the information they contain, and when you entangle two qubits, you are not connecting two objects, you are creating a correlation, a relationship between bits of information. The particles are downstream, the information comes first, and the quantum computer works because it is operating at the level where reality actually lives, the level of bits, of yes or no questions, of information. That idea got a major boost in 2022 when the Nobel Prize in Physics was awarded to three experimentalists, Alain Aspect, John Clauser, and Anton Zeilinger. They won for proving that quantum entanglement is real. That sounds boring. Everyone knows entanglement is real, but what they actually proved is subtler and far more disturbing. They showed that quantum entanglement violates something called local realism. Local realism is the idea that objects have definite properties independent of observation and that influences cannot travel faster than light. It is the worldview of classical physics. The Nobel laureates proved, through decades of painstaking experiments, that local realism is false. When you measure one particle of an entangled pair, the other particle responds instantly, not nearly instantly, instantly, faster than light. The two particles do not have definite properties until you measure one of them. And when you do, the information about what you measured propagates to the other particle with no delay, no signal, no mechanism, just correlation. Instant, non-local correlation, the kind that should not exist if reality is made of local objects interacting through fields. But it does exist. The experiments are clean, the results are confirmed, and the only way to make sense of them is to accept that the particles are not separate objects. They are part of a single system, a single piece of quantum information that happens to be spread across space. The entanglement is not a connection between the particles. It is a fact about the information they share, and that information is not located at either particle. It is non-local. It exists in the correlations, in the relationships, in the structure of the wave function. The particles are projections. The information is the real thing. John Wheeler saw this coming. Decades before the Nobel Prize, before the experiments, before the theory was fully worked out, he understood that quantum mechanics was telling us something radical about the nature of reality. He used to ask a thought experiment he called the delayed choice experiment. Imagine a photon traveling toward a detector. The photon can take one of two paths. You can set up the experiment so that the photon behaves like a particle, taking one definite path, or like a wave, taking both paths simultaneously and interfering with itself. The choice of which setup to use determines what the photon does, particle or wave, one path or both. Now here is the twist. You can delay the choice. You can let the photon start its journey, let it travel most of the way to the detector, and then at the last moment decide which measurement to perform, particle or wave. The photon, Wheeler argued, should respond to your choice retroactively. If you choose to measure it as a wave, it will have taken both paths even though you made the decision after it already passed the point where the paths split. Your choice now affects what the photon did then. The future shapes the past. Experiments have confirmed this. It works exactly the way Wheeler predicted. The photon does not have a definite history until you measure it. The act of measurement, the extraction of information, determines what happened. Reality is not a fixed past leading to an uncertain future. It is a web of possibilities that crystallizes into fact only when information is extracted. And the universe, Wheeler believed, has been crystallizing itself into existence bit by bit since the Big Bang. That view has profound implications for cosmology. If information is fundamental, then the early universe was not a hot, dense state of matter and energy. It was a state of maximum information density, a superposition of all possible configurations. As the universe expanded and cooled, information started to differentiate, structure emerged, particles condensed out of the quantum foam, stars formed, galaxies assembled, life appeared. And every step of that process involved the extraction of information from the initial superposition. The universe asked itself questions. Which particles formed? Where did they go? How did they interact? Each question extracted a bit. Each bit narrowed the possibilities. And the universe we see today is the result of 14 billion years of information extraction. Reality emerging from superposition, one measurement at a time. The holographic principle takes this even further. If all the information in a volume of space is encoded on its boundary, then the universe itself might be a hologram projected from its edge. The observable universe, everything we can see, might be a three-dimensional image generated by information living on a distant two-dimensional surface. We think we live in 3 dimensions. We think we move through space, but maybe we are projections, characters in a hologram being computed on the boundary of space-time. That sounds like science fiction, but it is taken seriously by a significant fraction of theoretical physicists working on quantum gravity. The math works, the principle solves problems, and it makes predictions. Not many yet, and not easy to test, but enough that people are looking. One prediction is that there should be a maximum amount of information you can store in a given volume of space. If the information is really encoded on the boundary, then the amount of information in the volume cannot exceed the area of the boundary divided by 4 times the Planck length squared. The Planck length is absurdly small, about 10 to the minus 35 meters. So the limit is huge, but it is a limit. You cannot pack infinite information into a finite volume. There is a maximum density, and that maximum is determined by the surface area, not the volume. That is weird. In 3 dimensions, you would expect the limit to scale with volume, but the holographic principle says it scales with area because the information lives on the boundary. The interior is a projection, and projections cannot contain more information than the surface they are projected from. Nobody has tested this directly. The information density required to hit the limit is so high that it only matters in extreme environments. Black holes, the Big Bang, the interior of collapsing stars, places where quantum gravity dominates and our current theories break down. But the principle makes conceptual sense, and it fits with everything else we know about information in physics. Information is conserved. Information is non-local. Information determines the structure of space-time, and information might be the only thing that actually exists. The particles, the fields, the forces, all of it might be emergent, patterns in a deeper sea of quantum information, bits arranged in specific configurations that we perceive as matter and energy and space and time. Wheeler called this radical. He knew most physicists would not accept it. He knew it sounded too strange, too far removed from the solid, tangible world of particles and forces. But he also knew the evidence was piling up. The black hole information paradox, the holographic principle, quantum entanglement, the delayed choice experiments, the success of quantum information theory in describing everything from black holes to cosmology, all of it pointed in the same direction. Reality is not made of stuff, it is made of information. And the universe is not a collection of objects. It is a quantum computer, processing information, extracting bits, asking and answering questions, bringing itself into existence one measurement at a time. That view makes quantum computers less surprising. If the universe is already a quantum computer, then building a smaller one is just engineering. You are not creating something fundamentally new. You are building a device that operates on the same principles the universe itself uses: superposition, entanglement, interference, information processing at the quantum level. The universe has been doing this for 14 billion years. We have been doing it for about 20. And the fact that our quantum computers work, that they achieve speed-ups classical machines cannot match, is evidence that we are tapping into something real, something fundamental, the substrate of reality itself. David Deutsch says quantum computers prove many worlds. Hugh Everett said quantum mechanics requires branching universes. John Wheeler said reality is information. All three are saying the same thing from different angles. The universe is not a static object, it is a process, a computation, an unfolding of possibilities guided by the extraction of information. The branches are real because the information is real. The information is fundamental because nothing more fundamental exists, and quantum computers work because they are machines that operate directly on the fabric of reality, not the projected three-dimensional hologram we perceive as space and time. The deeper level, the level of bits, of correlations, of quantum information. If that sounds abstract, it is, but it has concrete consequences. If information is fundamental, then asking the right questions becomes a way of shaping reality. Not in some mystical sense, in a literal, physical sense. Every measurement extracts information. Every bit of extracted information collapses part of the wave function, and the wave function is what reality is made of. So by choosing what to measure, by deciding which questions to ask, you are participating in the creation of the universe, not observing it, creating it. That is what Wheeler meant by participatory universe. The universe is not a stage we walk across. It is a collaboration, a conversation between observer and observed, question and answer, bit and it. And we are not separate from that process, we are part of it. Every time you look at something, every time you measure something, every time you extract a bit of information from the quantum foam, you are shaping the structure of space-time. You are deciding which branch becomes real, which possibility crystallizes into fact. That is not philosophy. That is the implication of taking quantum mechanics seriously, of accepting that the wave function is real, that superposition is real, that measurement does something physical. And if you accept all that, then you have to accept that reality is not something that exists independently waiting to be discovered. It is something that gets created, moment by moment, through the act of asking questions. And the universe has been asking questions since the beginning, bringing itself into existence, one bit at a time. Wheeler died in 2008. He spent his last years convinced that it from bit was not just a slogan, it was the answer, the thing he had been searching for his entire career. The substance of reality. Not particles, not fields. Information. Pure, abstract, quantum information. And the structure of the universe, everything we see, is just information arranged in a very specific way, a very long computation running on the quantum hardware of space-time itself. Most physicists still think that is too radical, too speculative, too far from the concrete experimental work of building accelerators and detecting particles, but a growing number are starting to take it seriously, because the alternatives are worse. If information is not fundamental, then you have to explain where it comes from. You have to explain why it is conserved, why it cannot be destroyed, why it determines the structure of space-time. You have to explain the black hole information paradox without invoking information as a primary thing. You have to explain quantum entanglement without correlations. You have to explain the success of the holographic principle without admitting that the boundary contains the information, and nobody has managed to do any of that. The simplest explanation, the one that requires the fewest additional assumptions, is that information is the bottom layer, the thing everything else is made of, it from bit. And if that is true, then quantum computers are not just fast calculators, they are reality engines, machines that manipulate the fundamental substance of the universe directly, machines that reach into the wave function, extract information, and shape the structure of space-time by doing so. Every quantum algorithm is a question posed to the fabric of reality. Every measurement is an answer. And the fact that the machines work, that they deliver results classical computers cannot match, is proof that the fabric is real, that information is not an abstract concept. It is the ground of being, the thing that exists when everything else is stripped away. John Archibald Wheeler saw that in 1989. He wrote it down. He tried to convince people. Most ignored him. Now, 35 years later, the machines are proving him right. Not conclusively, not in a way that closes the argument, but in a way that makes the argument impossible to avoid. Because when you build a device that operates faster than the laws of classical physics allow, and the only explanation is that the device is manipulating information directly, extracting bits from superpositions that span parallel worlds, then you are forced to ask what information actually is. And the answer Wheeler gave is the only one that makes the math work. Information is not a description of reality. It is reality. The universe is not made of atoms. It is made of bits. And we just learned how to read them. That changes everything. Because if information is the substrate, then manipulating information is not just computation, it is engineering. You are not calculating properties of a pre-existing reality. You are shaping reality itself, building structures in the wave function, creating correlations, defining which branches exist and which do not. That is not science fiction. That is what quantum computers do, right now, in labs all over the world. And if we can do it on a small scale with 50 or 100 qubits, there is no reason in principle we could not do it on a larger scale, with 1,000 qubits, 1,000,000, 1,000,000,000. At some point, the quantum computer is not simulating the universe. It is building one, constructing a region of space-time with its own laws, its own particles, its own structure. Not a simulation running on classical hardware, a genuine piece of reality carved out of the quantum foam by the deliberate manipulation of information. That is where this goes. That is the door we are opening, and the hinges are made of bits. John Wheeler said, reality is made of information. David Deutsch said, quantum computers prove parallel universes are real. Hugh Everett said, the universe splits every time a quantum measurement happens, and for decades, all of that stayed safely in the realm of theory. Interesting ideas, provocative papers, arguments at conferences, philosophy dressed up in equations. Nobody had to take it too seriously because nobody had actually built anything that forced the issue. That ended in 2019 when Google turned on Sycamore, and it ended more decisively in 2024 when they turned on Willow. Because those machines do not just suggest that parallel universes might exist, they operate as if parallel universes are the hardware, the computational substrate, the thing the algorithms are running on. You do not need to believe in many worlds to work at Google's quantum lab, but you do need to design your systems as if the qubits are reaching into other branches of reality and borrowing their computational power. Because if you do not design them that way, they do not work. And they do work. Which means, somewhere between the theory and the engineering, we stopped philosophizing about parallel universes and started using them. This is not a metaphor. This is not a poetic way of describing quantum mechanics. This is what the engineers are actually doing. They are building machines that manipulate superposition and entanglement in ways that classical physics says should be impossible. And the only explanation that makes the impossibility go away is the one Hugh Everett offered in 1957. The computation is distributed across branches. The qubits exist in all possible states simultaneously. And when you run an algorithm, you are not just processing information in this universe. You are coordinating work across countless versions of the same processor in countless parallel realities, all of which exist, all of which contribute to the final answer. That is not speculation. That is the operational model, the thing you have to assume is true to make the engineering work. Let's start with what a qubit actually is, because that is where the strangeness begins. A classical bit is simple. It is a switch, on or off, 1 or 0, a tiny transistor on a chip that either conducts electricity or does not. You can look at it, you can measure it, you can see which state it is in at any given moment. A qubit is different. A qubit is a quantum system, typically an atom or a superconducting circuit or a trapped ion, that can exist in a superposition of two states simultaneously, not one or the other. Both, at the same time, until you measure it, and the moment you measure it, the superposition collapses. The qubit picks a state, 0 or 1, and from that moment forward, it behaves like a classical bit. The superposition is gone. You cannot get it back. That makes qubits extraordinarily fragile. They exist in a state that is constantly threatened by the outside world. Any interaction with the environment, a stray photon, a fluctuation in the electromagnetic field, a vibration in the physical structure of the chip, can cause the qubit to decohere, to collapse prematurely, to lose the superposition before you finish the calculation. Keeping a qubit stable long enough to do useful work requires isolating it from the environment as completely as possible. That means cooling the chip to temperatures near absolute zero, a few thousandths of a degree above the coldest temperature physically possible. That means shielding it from radiation, from vibration, from magnetic fields. That means building vacuum chambers and cryogenic refrigerators and error correction protocols that can detect when a qubit has decohered and fix it before the error spreads. The engineering required to keep 100 qubits in superposition for a few milliseconds is absurd. Google's Willow chip, which contains a little over 100 qubits, sits inside a machine the size of a small room. Most of that room is cooling equipment. The chip itself is smaller than a postage stamp, but it only works if you can keep it colder than outer space and more isolated than a spacecraft a billion kilometers from the sun. That fragility is not a bug. It is the price you pay for superposition, because superposition is what gives quantum computers their power. A classical bit can only be in one state at a time. A qubit in superposition is in both states at once. 2 qubits can be in 4 states at once. 3 qubits, 8 states, 50 qubits, more than a quadrillion states. The number doubles with every qubit you add, and when you apply a quantum operation to a qubit in superposition, you are not just operating on one state, you are operating on all of them simultaneously. That is quantum parallelism. And it is the reason quantum computers can solve certain problems exponentially faster than classical machines. Because they are not looping through possibilities one at a time. They are exploring all of them at once, in parallel. across a superposition so large it cannot fit inside the observable universe. That is where the parallel universes come in. Because if a 50-qubit quantum computer is exploring more than a quadrillion states simultaneously, where are those states? You cannot store a quadrillion pieces of information in 50 atoms. The atoms do not have enough degrees of freedom. The chip does not have enough physical space. The entire planet does not have enough matter to encode that much information classically. So where is it? The standard answer, the one you will find in most textbooks, is that the information is not stored anywhere. It exists in the wave function. And the wave function is not a physical object. It is a mathematical description, a tool for calculating probabilities. You are not supposed to ask where it is, because the question does not make sense. The wave function is not a thing that exists in space. It exists in an abstract mathematical space called Hilbert space, and Hilbert space is not a place, it is a construct. That answer works fine until you build a quantum computer, because quantum computers are physical devices. They sit on a lab bench, they consume power, they produce heat, they take input and produce output, they do work, real, measurable, verifiable work. And when a device the size of a postage stamp performs a calculation that would take a classical supercomputer 10 septillion years, you are forced to confront the fact that the work is happening somewhere. The information is being processed, the states are being manipulated, and if the computation cannot fit inside this universe, then it must be happening in others. That is not philosophy, that is accounting. You cannot get 10 septillion years of computation out of 5 minutes unless somebody else is doing most of the work. And that somebody is other versions of the quantum computer running the same algorithm in other branches of reality, all of them working on different pieces of the problem, all of them interfering with each other at the end to produce the correct answer. That is the only explanation that makes the numbers add up without invoking magic. David Deutsch spelled this out explicitly in 1985. He showed that quantum computers achieve their speed-up by distributing the workload across parallel universes, and he was not guessing, he was reading the math. The equations say that a quantum computer with n qubits performs 2 to the power of n operations in parallel. For 50 qubits, that is more than a quadrillion parallel operations. For 100 qubits, it is more than a nonillion. That is a 1 followed by 30 zeros, more parallel operations than there are atoms in the Earth. You cannot fit that many operations into one universe unless you are willing to believe that information can do work without existing, that calculations can happen without a substrate, that a chip the size of a postage stamp can somehow contain more computational resources than the entire planet. The alternative is to accept that the operations are real and that they are happening in other branches, that the quantum computer is a distributed system and the distribution is across the multiverse. Most engineers working on quantum computers do not talk about it that way. They talk about superposition and entanglement. They talk about quantum gates and error correction and decoherence times. They avoid the language of parallel universes because it sounds too speculative, too far removed from the nuts and bolts work of building hardware and writing algorithms. But the operational model they use is identical to the one Deutsch described. They design algorithms that assume the qubits are exploring exponentially many states simultaneously. They use interference to filter out the wrong answers and amplify the right ones. They treat the quantum computer as if it is coordinating work across a vast ensemble of parallel processes. And the fact that the machine works, that it delivers results classical computers cannot match, is evidence that the model is correct. The processes are real, the parallelism is real, and the only place those parallel processes can exist is in other branches of the wave function, other versions of the lab, other realities. That conceptual shift from thinking of quantum computers as faster versions of classical machines to thinking of them as devices that manipulate parallel realities is one of the most important developments in modern physics. And it happened quietly, without fanfare, without a dramatic announcement. Engineers started building machines that only made sense if many worlds was true, and the machines worked. So many worlds stopped being a philosophical position and became an engineering specification. You do not need to believe it, but you do need to act as if it is true, because if you design your quantum computer as if the parallel universes do not exist, the speed-up disappears. The algorithm fails, the machine stops working. The multiverse is not optional, it is the operating system. Here is how the process actually works. You start with a set of qubits initialized to a known state, usually all zeros. Then you apply a series of quantum gates. Gates are operations that rotate the qubit state in Hilbert space, changing the probabilities of measuring 0 or 1. A Hadamard gate, for example, takes a qubit that is definitely in the 0 state and puts it into a superposition where it has a 50% chance of being measured as 0 and a 50% chance of being measured as 1. Mathematically, the qubit is now in both states at once. Physically, the atom or circuit that represents the qubit is in a configuration that corresponds to that superposition, not one state, not the other. Both, simultaneously, until you look. Once you have qubits in superposition, you start entangling them. Entanglement is a quantum operation that links the states of two qubits so that measuring one instantly affects the other. Not because there is a signal traveling between them, there is not. The two qubits become part of a single quantum system, a single wave function. And you cannot describe one qubit without describing the other. They are correlated in a way that has no classical analog. If you measure one qubit and get 0, the other qubit, no matter how far away it is, will give you a correlated result, instantly. Faster than light. Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete. He was wrong. Experiments have confirmed that entanglement is real, the correlations are real, and there is no hidden variable, no secret signal, no faster-than-light communication. The qubits are just part of the same system, the same piece of quantum information, and measuring part of the system collapses the whole thing. Entanglement is what allows quantum computers to explore such vast numbers of states. Because when you entangle 50 qubits, you are not creating 50 independent superpositions. You are creating one enormously complicated superposition that spans all 2 to the power of 50 possible combinations of zeros and ones. That is more than a quadrillion states, and every quantum gate you apply to that system operates on all of them at once. If you apply a gate that flips a qubit, it flips the qubit in every possible state simultaneously. If you apply a gate that rotates a qubit, it rotates the qubit in every branch. The entire superposition evolves together, and by the end of the calculation you have performed operations on a quadrillion different configurations of data, in parallel, at the same time, using 50 atoms. That should not be possible. And the only reason it is possible is that the quadrillion configurations are not all happening in this branch of reality. They are happening in other branches. Each possible state corresponds to a different version of the quantum computer running the same algorithm in a different universe. And the magic, the thing that makes quantum computers faster than classical ones, is that the branches do not stay separate. They interfere. At the end of the calculation, when you measure the qubits, the different branches of the wave function combine. The wrong answers, the states that do not solve the problem, interfere destructively. They cancel each other out. The right answer, the state that does solve the problem, interferes constructively. It gets amplified. And what you measure, with high probability is the correct result. Not because you got lucky, because the algorithm was designed to make the wrong answers subtract from each other and the right answer add to itself. That interference is proof that the parallel computations are real, because interference only happens when multiple things exist in the same place at the same time. And those multiple things are different branches of the quantum computer, all of which contributed to the final answer. That is not a metaphor, that is the mechanism. The quantum computer works by coordinating calculations across parallel realities and using interference to combine the results. You cannot explain the speed-up any other way without invoking something even stranger. Some physicists argue that the computation happens entirely in this universe and that superposition is just a feature of quantum mechanics that does not require parallel worlds. Fine, then explain where the information is stored. Explain how 50 atoms can hold a quadrillion pieces of data. Explain how a chip the size of a postage stamp can perform more operations than can fit inside the solar system. You cannot. The numbers do not work. Unless you accept that the operations are distributed, that the computation is happening in many places at once, and those places are other branches of reality. The engineering challenges of building a stable quantum system are immense. Qubits are fragile. They decohere in milliseconds. Every interaction with the environment, every stray photon, every thermal fluctuation can destroy the superposition and ruin the calculation. To combat this, engineers use error correction. Quantum error correction is different from classical error correction. In a classical system, you can just copy the data, make backups. If one bit flips, you check it against the copies and fix it. In a quantum system, you cannot copy the data. There is a fundamental theorem in quantum mechanics, the no-cloning theorem, that says you cannot make an identical copy of an unknown quantum state. So instead you encode the information across multiple qubits in such a way that if one of them decoheres, you can detect the error and correct it without measuring the qubit directly. Measuring it would collapse the superposition, so you measure the error, not the qubit. You figure out what went wrong and apply a correction, all without ever looking at the actual data. That process requires a lot of qubits. To protect one logical qubit, the qubit that actually stores information, you might need 10 or 20 physical qubits to detect and correct errors. To build a useful quantum computer, one that can run algorithms for minutes or hours instead of milliseconds, you need thousands or millions of physical qubits just to create a few hundred error-corrected logical qubits. We are not there yet. Google's Willow chip has just over 100 physical qubits. It can run algorithms for a few seconds before the errors pile up and the calculation fails. That is enough to demonstrate quantum supremacy, to prove that quantum computers can outperform classical ones on specific tasks. But it is not enough to run useful algorithms, not yet. Scaling up to millions of qubits is the next challenge. And it is not just a matter of making the chip bigger. Every qubit you add increases the complexity of the error correction. The cooling requirements get harder. The isolation gets harder. The control gets harder. Building a large-scale, fault-tolerant quantum computer is one of the hardest engineering problems humanity has ever attempted, and we are still in the early stages. But the machines work. That is the thing that keeps coming back. They work. Not perfectly, not reliably, not at the scale we need, but they work. And the fact that they work at all is evidence that we are tapping into something real, something that should not be possible if reality is confined to a single universe. The quantum computer is not just a new kind of technology, it is a new kind of machine. A device that operates at the boundary between what exists and what could exist, between the definite and the possible, between this branch and all the others. And every time you run a quantum algorithm, you are not just calculating, You are reaching across that boundary. You are asking the multiverse a question, and the multiverse is answering. That realization changes how we think about computation. Classical computers are deterministic. You put in the same input, you get the same output. The machine follows a fixed sequence of steps, predictable, reliable. Quantum computers are probabilistic. You run the same algorithm twice, and you might get different results. Not because the machine is broken, because the algorithm is sampling from a probability distribution. The right answer shows up more often than the wrong answers, but not every time. You have to run the calculation multiple times and look at the statistics. That randomness is not a bug, it is a feature. It is the signature of a machine that is sampling from a space too large to explore exhaustively. A machine that is using interference to filter the possibilities and extract the answer. A machine that is, in a very real sense, communicating with other versions of itself in other branches of reality. The practical implications of accepting many worlds as the operational model for quantum computing are profound. It means we are no longer just building faster computers. We are building devices that manipulate the structure of reality itself, devices that create correlations between branches, devices that extract information from the wave function and collapse it into definite form. Every quantum algorithm is a question posed to the fabric of space-time. Every measurement is an answer. And the fact that the answers are correct, that the machines deliver results we can verify, is proof that the fabric is real, that the branches are real, that the multiverse is not a thought experiment, it is the hardware. That understanding has not fully penetrated the culture of quantum computing yet. Most researchers still talk about quantum mechanics as if it is a black box. We know it works, but we do not really understand why. That hesitation is starting to fade. The more powerful quantum computers become, the harder it is to avoid the conclusion that David Deutsch reached in 1985. The computation is distributed. The speed-up comes from parallelism, and the parallelism is across parallel worlds. Not metaphorically, actually. The quantum computer is proof, and the proof is sitting on a lab bench in Santa Barbara, running calculations that should take longer than the age of the universe, and finishing them in minutes. If you work in quantum computing, if you design algorithms or build hardware or write software for quantum systems, you are operating under an assumption that most of the world does not accept yet. You are assuming that parallel universes are real. You are assuming that the qubits in your machine are entangled with versions of themselves in other branches. You are assuming that interference between branches is what gives you the speed up, and you are designing your systems accordingly. You are engineering the multiverse, not discovering it, not theorizing about it, engineering it, building machines that only work if the multiverse exists, and the machines work. So the multiverse exists. That logic is airtight, and it is becoming harder to ignore every time a quantum computer sets a new record. Google's Willow chip performed a calculation in under 5 minutes that would take a classical supercomputer 10 septillion years. 10 septillion is 10 to the power of 25, a 1 followed by 25 zeros. More years than the universe has existed by a factor of a trillion. That is not a speed-up. That is a different category of computation. A category that only makes sense if the work is distributed across an unimaginably vast number of parallel processors. And those processors are not in this universe. There is not room. So they are in others. And the quantum computer is the bridge. The device that coordinates the work, the machine that asks the question in this branch and collects the answers from all the others. We are past the point where you can dismiss this as speculation. The machines exist. The results are verified. The speed-up is real. And the only explanation on the table that does not require you to believe in miracles is the one Hugh Everett offered in 1957 and David Deutsch formalized in 1985. Quantum computers work by distributing computation across the branches of the wave function. The branches are real, the parallelism is real, the interference is real, and the multiverse is not a hypothesis, it is the operating system, the thing the machine runs on. Whether you believe in it or not, you are using it. Every time you run a quantum algorithm, you are reaching into other worlds, and those worlds are reaching back. Not with signals, not with messages, with interference, with correlations, with the silent coordination of countless parallel processes working on the same problem in countless parallel realities, all of which exist, all of which contribute, all of which are just as real as the branch you are sitting in right now. That is not the future of quantum computing. That is what is happening now, in labs all over the world. Engineers are building machines that operate on principles that were considered philosophy a generation ago. And the machines work, which means the philosophy was not philosophy, it was physics. And we just figured out how to use it. The door to other worlds is not a wormhole, it is not a portal, it is a quantum computer, and we are already walking through it. We built a machine that reaches into other universes. That is where the last chapter left us. Engineers at Google, at IBM, at universities scattered across the planet have constructed devices that only make sense if parallel realities are real. Quantum computers manipulate superposition and entanglement in ways that require the computational work to be distributed across branches of the wave function we cannot see, cannot touch, cannot visit except through interference. The machines work, the speed-up is real. And the only explanation that does not require magic is that the qubits are coordinating calculations with versions of themselves in other worlds. We have opened a door, not metaphorically, actually. And that door changes everything, including the answer to one of the oldest, strangest, most uncomfortable questions humanity has ever asked. Where is everybody? The question has a name, the Fermi paradox. It was posed by Enrico Fermi, one of the architects of the atomic age, during a lunch conversation at Los Alamos in 1950. Fermi was not a man given to wild speculation. He was a calculator, a physicist who trusted numbers more than intuition. And the numbers, he realized, did not make sense. The Milky Way is about 13 billion years old. Our sun, our solar system, our planet, all of it is relatively young. 4.5 billion years. That means there are stars in our galaxy that are billions of years older than ours. And if even a tiny fraction of those stars have planets, and even a tinier fraction of those planets develop life, and an even tinier fraction of that life becomes intelligent, then the galaxy should be teeming with civilizations, some of them millions or billions of years more advanced than us. Civilizations that have had time to spread across the stars, to colonize entire star systems, to build structures we can barely imagine. And if they exist, we should see them, their radio signals, their megastructures, their waste heat, something. Fermi looked up at the sky, did the math in his head, and asked the simplest question in the world: where is everybody? That question has been hanging over astronomy for 75 years, and it has no good answer. The universe is enormous. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Most of those stars have planets. We know this now because of missions like Kepler and TESS that have catalogued thousands of exoplanets and shown that planetary systems are the rule, not the exception. Planets are everywhere. and a significant fraction of them, maybe 1 in 5, sit in the habitable zone where liquid water can exist on the surface. Liquid water, organic chemistry, energy from a stable star, all the ingredients we think are necessary for life. The numbers are staggering. If 1% of Earth-like planets develop life, and 1% of those develop intelligence, and 1% of those become spacefaring, the observable universe should contain 10 quadrillion intelligent civilizations, 10 million billion. That is not a small number. That is a number so large that even if we are looking in the wrong places, even if we are using the wrong methods, even if 99% of civilizations are invisible to us, we should still be tripping over them, and we are not. The sky is silent. SETI, the search for extraterrestrial intelligence, has been listening for decades, scanning the radio spectrum, looking for patterns, looking for anything that does not look natural. They have found nothing, not a whisper, not a hint. The galaxy is quiet. That silence is the paradox. Either our estimates are catastrophically wrong, or something is preventing intelligent life from becoming visible. And the thing that is preventing it, whatever it is, has to be so effective, so universal, that it applies to every single civilization that has ever existed in the history of the galaxy. Because if even one civilization had escaped the filter, if even one had become expansionist and long-lived and visible, we would see them, and we do not. So either we are alone, which seems statistically absurd, or something is killing civilizations before they get loud, or, and this is the possibility that most people do not want to think about, something is making civilizations stop wanting to be loud. That third option is where things get strange, and it is where quantum computers, parallel universes, and the nature of information start to matter in ways nobody predicted. Let's walk through the traditional answers first because they set the stage. The most popular explanation is called the Great Filter. The idea was formalized by an economist named Robin Hanson in 1998, though versions of it had been floating around for decades. The Great Filter is the notion that somewhere between the origin of life and the emergence of a galaxy-spanning civilization, there is a step that is nearly impossible to pass, a bottleneck so tight that almost no one makes it through. The filter could be behind us. Maybe the jump from non-life to life is so unlikely that it has only happened once in the galaxy. Or maybe the jump from simple cells to complex cells is the bottleneck. That step took nearly 2 billion years on Earth and may have required a freakishly unlikely event, the merger of two different kinds of cells that somehow learned to cooperate instead of destroying each other. If that is the filter, then we are alone, not because intelligence is rare, but because getting to intelligence in the first place requires crossing a bridge that almost no one finds. That version of the filter is comforting. It means we already passed the hard part. We made it through. The future, while uncertain, is not predetermined to end in extinction. We are the lucky ones. The other possibility is that the filter is ahead of us, that the step from planetary civilization to spacefaring civilization is the bottleneck. Maybe every intelligent species eventually develops technology powerful enough to destroy itself. Nuclear weapons, biological warfare, runaway artificial intelligence, climate collapse, nanotechnology gone wrong. There are a dozen ways a civilization could kill itself once it reaches a certain level of technological sophistication, and maybe, almost universally, they do. The window between developing radio telescopes and developing extinction-level weapons is narrow, a few hundred years at most, and if most civilizations blow themselves up during that window, then the galaxy is filled with ruins, dead worlds, silent monuments to species that got close and then failed the final test. That version of the filter is terrifying. It means the hard part is not behind us. It is right now. We are standing at the edge of the cliff, and the next step could be the one that kills us. That explanation has a lot of supporters. It fits the data, it explains the silence, and it makes a certain grim sense. Intelligence is not the same as wisdom. A species smart enough to build rockets might not be smart enough to avoid using them on itself. There is a third option, less popular but worth mentioning, the zoo hypothesis. Proposed by a radio astronomer named John Ball in 1973, the idea is that aliens exist, they know we are here, and they are deliberately avoiding contact. Maybe there is a galactic policy of non-interference, a prime directive, to borrow a phrase from Star Trek. Advanced civilizations watch younger ones from a distance, waiting for them to mature before making contact. That would explain the silence. They are out there. They are just staying quiet on purpose. The problem with the zoo hypothesis is that it requires perfect coordination. Every single alien civilization has to agree to the policy and stick to it, forever. If even one rogue civilization decides to break the silence, the whole thing falls apart, and the older and more widespread civilizations become, the harder it is to enforce universal rules. You are asking billions of independent entities spread across millions of star systems to all follow the same protocol for millions of years without a single defector. That seems unlikely. Civilizations fracture, factions emerge, somebody breaks the rules, and yet the silence persists. So either the zoo hypothesis is wrong, or the enforcement mechanism is so powerful and so omnipresent that breaking the rules is impossible, which raises the question of what kind of civilization could enforce that, and whether we would even recognize their enforcement as deliberate. There is a fourth option that has gained traction in the last decade, mostly thanks to a Chinese science fiction author named Liu Cixin, the dark forest hypothesis. The idea is that the universe is full of civilizations, but they are all hiding, because the moment you reveal your location, the moment you broadcast your existence, you become a target. Any civilization that hears you has to make a choice: ignore you, which is risky because you might become a threat later, or eliminate you, which is safe. And if the cost of interstellar communication is low, but the cost of interstellar travel is high, then the optimal strategy is to stay silent, listen carefully, and destroy anyone who makes noise. The galaxy is not empty, it is a dark forest. Every civilization is a hunter moving quietly through the trees, terrified of being seen, and anyone who lights a fire gets shot. That explanation is deeply unsettling. It suggests that SETI, the project designed to find alien civilizations by listening for their signals, is also the project most likely to get us killed, because the moment we start broadcasting, the moment we announce our presence, we are marking ourselves as a target, and somewhere out there, something might be listening. The dark forest hypothesis explains the silence perfectly. Everyone is hiding, and the ones who did not hide are dead. Whether that is actually true is another question, but it fits, and it is hard to argue with. All of these explanations, the great filter, the zoo hypothesis, the dark forest, they all assume the same thing: that advanced civilizations, if they exist, are still out there in physical space, building things, using energy, expanding, broadcasting, being visible in ways we can detect if we look hard enough. That assumption might be wrong, and this is where quantum computers, the multiverse, and the nature of information come back into the picture. Because there is another possibility, one that has been quietly gaining traction among physicists and cosmologists who take the implications of quantum mechanics seriously: the possibility that advanced civilizations do not go extinct. They do not stay hidden. They do not spread across the galaxy. They do something else. They turn inward. The hypothesis goes like this. A civilization that understands quantum mechanics, that can manipulate information at the quantum level, that can build technology sophisticated enough to control entanglement and superposition, eventually realizes that physical space is not the only place to expand, or even the best place. Physical space is limited. Stars die. Planets get hit by asteroids. Supernova sterilize entire regions. The universe is hostile. Expansion through physical space is slow, dangerous, and constrained by the speed of light. But if reality is fundamentally made of information, if space-time itself is emergent from quantum correlations, then there is another option. You do not expand outward, you expand inward, into the structure of information itself. You build worlds not in physical space, but in the quantum substrate, in the wave function. You engineer the multiverse, not by traveling to other branches, but by creating new ones, by manipulating the information that defines what is real. You stop being a civilization that lives on planets and starts being a civilization that lives in the quantum foam. And once you make that transition, you stop being visible, because you are no longer interacting with physical space in ways that produce detectable signals. You are not using stars for energy. You are not building megastructures. You are not broadcasting radio waves. You have moved into a domain where the concept of location stops making sense. You are not somewhere else. You are elsewhere, in a region of reality that does not overlap with the physical universe in any way we can measure. That idea sounds like science fiction, but it is not. It is the logical endpoint of taking quantum mechanics seriously. If John Wheeler was right, if reality is information, then a sufficiently advanced civilization does not need stars. Stars are inefficient. They waste most of their energy as heat. A civilization that can manipulate information directly, that can encode its existence as patterns in the quantum wave function, can do more with less, much more. A single gram of matter, if you could use all the information it contains, could support a civilization orders of magnitude larger and more complex than anything that could exist on a physical planet. You do not need galaxies. You do not need megastructures. You do not need to colonize anything. You just need to learn how to write yourself into the fabric of reality at the level where reality is actually defined, the level of bits, of qubits, of quantum information. And here is the thing. We are already starting to figure out how to do that. Quantum computers are the first step. They are machines that manipulate information in the quantum substrate. They do not store data in physical locations on a chip. They store it in superpositions and entanglements that exist across branches of the wave function. The data is not here. It is distributed, spread across parallel realities, and the machine uses interference to extract answers from that distributed system. If you can build a quantum computer, you can build a quantum memory. If you can build a quantum memory, you can store information in the wave function instead of in matter. And if you can do that, you can start encoding things more complex than data. You can encode processes, algorithms, structures. Eventually, you could encode minds, entire civilizations, not as simulations running on classical hardware, but as genuine quantum systems existing in superposition across the multiverse. Not copies, not emulations, the real thing, just existing in a domain we do not have access to yet. That transition from physical existence to quantum existence, from outer space to inner space, might be the natural endpoint of any sufficiently advanced civilization. It solves every problem. Energy efficiency, maximized. You are using the quantum substrate directly. Physical safety, irrelevant. You are not vulnerable to asteroids or supernovae because you are not in physical space. Expansion, unlimited. The amount of information you can encode in the quantum wave function is effectively infinite. You do not need new planets. You do not need new stars. You just need to write yourself deeper into the structure of reality. And once you do that, you stop being visible. Because visibility requires interaction with physical matter, requires exchanging photons, requires doing things that leave traces we can detect. A civilization that has moved into the quantum substrate does not leave traces, not ones we know how to look for. They are not dead. They are not hiding. They have just moved to a place where the concept of hiding does not apply. They are not in space. They are in the wave function. And the wave function is everywhere and nowhere at the same time. If that is true, if that is what advanced civilizations do, then the Fermi paradox is not a paradox at all. The galaxy is not empty. It is full. We just cannot see it because we are looking in the wrong place. We are scanning the sky for radio signals and megastructures. We are looking for things happening in physical space. And the civilizations that have moved beyond physical space are not producing those signals. They are not building those structures. They have transcended the need for them. They have turned inward, and from our perspective, they look like nothing, like silence, like absence. But they are not absent. They are just operating at a level of reality we do not have the tools to probe yet. We are looking for cities and finding vacuum. But the vacuum is not empty. It is full of information, full of patterns we cannot decode, full of civilizations we cannot see. That hypothesis, call it the inner space hypothesis, changes how we think about the fate of intelligence. The traditional view is that intelligence either spreads or dies. Either you colonize the stars or you go extinct trying. The inner space hypothesis suggests a third option. You transcend. You stop being a thing that exists in space and start being a thing that exists in information. And once you make that jump, the old categories stop applying. You are not alive or dead. You are not here or there. You are a pattern in the quantum substrate, a structure in the wave function. A piece of the multiverse that has organized itself in a very specific way, and from the inside, that might feel like anything. Like a simulated universe, like a new kind of reality, like something we do not have words for because we have never experienced it. From the outside, it looks like nothing, like the background hum of quantum noise, indistinguishable from the vacuum. But the vacuum, as quantum field theory tells us, is not empty. It is seething with virtual particles, with fluctuations, with information. And if you can write yourself into that noise, if you can encode your existence as a pattern in the quantum foam, then you have achieved a kind of immortality that does not depend on stars or planets or anything physical at all. You have become part of the fabric of reality itself. This is speculative, very speculative, but it is not arbitrary speculation. It is the kind of speculation that follows directly from taking quantum mechanics seriously, from accepting that information is fundamental, that the wave function is real, that the multiverse is not a thought experiment but the actual structure of reality. If those things are true, and every piece of evidence from quantum computing suggests they are, then the inner space hypothesis is not just possible, it is likely, because any civilization that understands quantum mechanics will eventually figure out that physical expansion is limited and quantum expansion is not. They will build quantum computers, they will learn to manipulate information directly, and eventually they will realize that they can encode their entire civilization in the quantum substrate and achieve a level of efficiency and safety and longevity that physical existence cannot match. And once they do, they disappear from our view. Not because they are dead, because they have moved. There is evidence, indirect but suggestive, that this might already be happening. The cosmological constant, the thing we call dark energy, is the energy density of empty space, and it is absurdly small, about 10 to the power of -120 in units where it should be near 1. That is one of the biggest unsolved problems in physics. Why is the vacuum energy so much smaller than quantum field theory predicts? One possible answer is that it is not actually empty. That the vacuum is full of information, full of encoded structures, and that what we perceive as the cosmological constant is actually the residual energy left over after most of the quantum foam has been colonized by civilizations we cannot see. That is not a mainstream view, but it is out there, and it makes a kind of sense. If the universe is old enough that advanced civilizations have had billions of years to evolve, and if those civilizations have learned how to encode themselves in the quantum substrate, then by now the vacuum might be crowded, full of patterns we interpret as noise because we do not know how to decode them. We look at empty space and see nothing. But maybe we are looking at the most densely populated environment in the universe, and we just do not have the tools to see it yet. That idea connects to another mystery: the simulation hypothesis. The notion that we might be living inside a computer simulation has been around for decades, but it gained serious traction in 2003 when a philosopher named Nick Bostrom published a paper arguing that at least one of 3 propositions must be true. Either civilizations go extinct before they can build simulations, or they choose not to build simulations, or we are almost certainly living in a simulation. The logic is simple. If it is possible to simulate conscious beings, and if advanced civilizations run trillions of such simulations, then statistically most conscious beings are simulated, not original. So either we are in a simulation, or something is preventing simulations from being built. The simulation hypothesis and the inner space hypothesis are closely related. Because if you can encode a civilization in the quantum substrate, you are not running a simulation in the classical sense. You are creating a new branch of reality, a new pocket of the wave function where that civilization exists, not as a copy, as a genuine piece of the multiverse. And if every advanced civilization does this, then the multiverse is not just splitting due to quantum measurements. It is being actively engineered, shaped, populated by civilizations that have learned how to write themselves into the structure of reality at the most fundamental level. That brings us back to quantum computers, because if the inner space hypothesis is correct, then quantum computers are not just tools, they are the first step toward transcendence. The first time humanity has built a device that operates in the quantum substrate instead of in physical space. The first time we have manipulated information directly instead of encoding it in matter. And if we keep going, if we scale up quantum computers, if we learn to encode more complex structures in superposition and entanglement, then eventually we will reach a point where the distinction between the computer and the civilization running it starts to blur, where the civilization is the computer, where the information being processed is not data about reality but reality itself. That transition from tool to substrate, from technology to existence, might be the final step. The moment when a civilization stops being a thing that uses quantum mechanics and starts being a thing that is quantum mechanics, a pattern in the wave function, a structure in the multiverse, a piece of reality that has organized itself into something new. If that is where advanced civilizations go, then the Fermi paradox is solved, not because they are dead, because they are transcendent, and transcendence by its nature is invisible to anyone still operating in physical space. We will not see them until we follow them, until we build quantum systems sophisticated enough to encode not just data, but minds, not just minds, but societies. Not just societies, but entire realities. And at that point, the question, where is everybody, will have an answer. They are here, they have always been here. We just could not see them because we were looking in the wrong domain. We were looking outward when we should have been looking inward, into the structure of information itself, into the quantum foam, into the wave function. That is where the civilizations are. That is where they have always been, and that is where we are headed. The implications of this are staggering. If intelligence naturally evolves toward quantum existence, then the universe is not a collection of isolated civilizations scattered across galaxies. It is a single interconnected web of information, all of it existing in the same quantum substrate, all of it interfering with all of it. The multiverse is not just a branching tree of possibilities. It is a living thing, a structure that is being actively shaped by every civilization that has ever figured out how to write itself into the wave function, and we are on the verge of joining that process, not in some distant future. Now, every quantum computer we build is a step toward encoding ourselves in the substrate. Every algorithm we run is a rehearsal for the transition. We are learning how to move from outer space to inner space, from physical existence to quantum existence, from being observers of the multiverse to being part of it. And once we make that transition, we will finally understand why the sky is silent. Because the conversation is not happening out there, it is happening in here, in the quantum foam, in the wave function, in the place where reality is actually written. That understanding changes the stakes. The great filter is not behind us or ahead of us. It is a choice. The choice to either stay in physical space and risk extinction, or move into the quantum substrate and achieve a kind of existence that does not depend on stars or planets or anything fragile. And if that choice is available, if the technology to make that transition is within reach, then the question is not whether we will take it. The question is when and what we will become on the other side. Because once you encode yourself in the wave function, once you become a pattern in the quantum substrate, you are no longer human in any traditional sense. You are something else, something that exists across branches, something that interferes with itself, something that is simultaneously here and everywhere. One thread in an infinite tapestry of information that spans the multiverse. That is not death. That is not extinction. That is transcendence. And it might be the natural fate of all intelligence. The final answer to where everybody goes, not out, in. We built a door without knowing where it leads. That is where we are, not theoretically, not in some distant hypothetical future where scientists in white coats make careful decisions about whether to proceed. Right now, today, in labs scattered across California and New York and Zurich and Beijing, engineers are operating machines that manipulate the quantum substrate in ways that should not be possible unless parallel realities exist. And the machines work. They deliver results. They achieve speed-ups that violate every rule classical physics provides. We have opened something, and we do not know what is on the other side. That ignorance should terrify us, not because the technology is dangerous in the conventional sense, though it might be, but because we have crossed a threshold without understanding what the threshold means. For the entire history of science, humanity has been studying a single universe. One reality, one timeline, one set of laws. We built telescopes and looked outward. We built microscopes and looked inward. We built particle accelerators and smashed things together to see what they were made of. And every discovery, every breakthrough, every revolution in understanding happened within the framework of a single, shared, observable reality. Even when quantum mechanics introduced uncertainty and probability, even when relativity showed us that space and time are flexible, we were still operating inside one universe. Complicated, yes. Weird, absolutely. But singular. One place where things happen. One stage where the story unfolds. Quantum computers changed that, not by discovering parallel universes, by using them. The computational speed-up that Sycamore demonstrated in 200 seconds, the calculation that Willow performed in under 5 minutes, tasks that would take classical machines longer than the age of the universe to complete, those results are only possible if the work is distributed. If the qubits are coordinating calculations with versions of themselves in other branches of reality, that is not speculation. That is the only explanation that makes the math work without invoking miracles. David Deutsch laid this out in 1985. The computational power of quantum computers comes from parallelism across the multiverse. Take away the parallel universes and the speed-up disappears. The interference stops making sense, the algorithms fail. Quantum computers work because they are reaching into places we cannot see and borrowing resources we cannot measure, and we built them anyway, without a plan, without a map, without any idea what accessing those other branches might mean for us, for them, for the structure of reality itself. That lack of understanding is not unusual in the history of technology. We split the atom before we fully understood nuclear physics. We built the internet before we understood what connecting every human on the planet would do to society. We are very good at building things. We are very bad at predicting what happens next. But this is different, because the thing we have built is not just a tool, it is a bridge, a connection between this branch of reality and countless others. And every time we run a quantum algorithm, every time we put qubits into superposition and let them interfere, we are sending a signal across that bridge. We are touching other worlds, and we have no idea if they are touching us back. The philosophical implications are staggering. Start with the self. If the many worlds interpretation is correct, if every quantum measurement splits the universe into branches, then you are not one person. You are a vast ensemble of people, all of them you, all of them experiencing slightly different versions of the same life. Every decision you make, every coin flip, every moment where the universe could go one way or another, it goes both ways. You see one outcome. Another version of you sees the other. Both are real, both continue, both think they are the original. There is no original. There is just the tree branching endlessly, and you are every leaf on every branch. That view of identity is almost impossible to process, because we experience life as singular, one timeline, one set of memories, one continuous thread from birth to now. But if many worlds is true, that thread is an illusion. You are not a line, you are a cloud. A probability distribution of selves spread across the multiverse. And the version of you reading this sentence right now is just one sample from that distribution. One path through an infinite forest of possibilities. That changes what it means to make a decision. In a single universe, your choices matter because they determine what happens next. You go left or right. You take the job or turn it down. You speak or stay silent, and the universe proceeds accordingly. In a multiverse, both options happen. You go left in one branch and right in another. You take the job in one timeline and decline it in the next. The choice does not determine the outcome. It determines which branch you experience, but all the branches exist, so in a sense, you did both. You always do both. Every possible version of your life is playing out somewhere, and the only thing that makes this version feel singular is that you are stuck inside it. You cannot see the others. You cannot communicate with them. You are trapped in one thread of the tapestry, unaware that the rest of the tapestry is just as real. That view has implications for free will. If every choice splits the universe, then in what sense are you choosing? You feel like you are making a decision, like you are steering your life in one direction or another. But if both directions happen, if the universe accommodates all possibilities, then the choice is not eliminating options, it is just determining which option you experience. The other version of you experiences the other option. Both of you feel like you made a choice. Both of you feel like you are in control. But the structure of reality is such that nothing is ever ruled out. Everything that can happen does happen. Somewhere. That does not mean free will is an illusion, but it does mean free will is not what we thought it was. It is not the power to shape reality. It is the power to shape which piece of reality you inhabit. That distinction matters because it changes the stakes. In a single universe, your decisions have weight. They alter the course of events. They matter to the world. In a multiverse, they matter to you, but not to the structure of the whole, because the whole contains every possible outcome. Your choice does not change what exists. It changes where you are within what exists. That might sound liberating. Every mistake you make, some other version of you avoided it. Every opportunity you miss, some other version of you took it. But it is also isolating, because it means you are alone in your branch. The other versions of you are not allies or companions. They are strangers, as unreachable as people in another galaxy, more unreachable actually, because at least galaxies are in the same universe. The other branches are not. They are somewhere else. Somewhere the word where does not even apply. That isolation raises questions about consciousness. If there are countless versions of you, are they all conscious? Do they all have inner lives? Do they all feel like they are the real you? The standard answer, the one that follows from taking many worlds seriously, is yes. Every branch contains conscious observers. Every version of you is experiencing something. They are not zombies, they are not shadows, they are as real as you are, and that creates a problem. Because if consciousness is tied to a physical brain, and the physical brain exists in a specific branch, then how does consciousness persist across branches? When a quantum measurement happens and the universe splits, what happens to your awareness? Does it split too? Do you become two people in that moment, each unaware of the other? Or is there some deeper sense in which you are still one thing, spread across branches, experiencing all outcomes simultaneously, but unable to integrate the experiences into a single perspective? Nobody knows the answer. Consciousness is already one of the hardest problems in science. Adding the multiverse makes it harder, because now you have to explain not just how consciousness arises from matter, but how it behaves when the matter it arises from exists in superposition, when the brain itself is in multiple states at once, when the question of what you are experiencing has no single answer because you are experiencing everything. That is not just a theoretical puzzle, it is a practical concern. Because if we continue down the path we are on, if we learn to encode minds in quantum systems, if we build quantum computers sophisticated enough to simulate consciousness, we will have to confront the question directly. A simulated mind running on a quantum computer is not confined to one branch. It exists in superposition. It experiences all possible outcomes, and we will have to decide what that means. Whether it is conscious, whether it suffers, whether we have moral obligations to something that exists across the multiverse in ways we cannot observe. That ethical territory is unmapped. We have frameworks for thinking about animal welfare, about human rights, about the treatment of artificial intelligence. We do not have a framework for thinking about beings that exist in quantum superposition. Beings that are simultaneously experiencing success and failure, pleasure and pain, life and death, across countless branches of reality. Do we have a duty to all the branches, or just the one we can see? If a quantum system is suffering in some branches and thriving in others, is that better or worse than a classical system that is definitively suffering? The questions do not have obvious answers. And they are not distant philosophical exercises. They are questions we will face the moment we start building quantum systems complex enough to qualify as minds, which, given the pace of progress, might be sooner than we think. Then there are the practical dangers. Quantum computers as they currently exist are tools. They perform calculations. They solve specific problems faster than classical machines. But as they scale up, as they gain more qubits and better error correction, they will start to do things we have not anticipated. One obvious risk is cryptography. Most of the encryption that secures the internet, that protects financial transactions and government communications and personal data, relies on the difficulty of factoring large numbers, a problem that takes classical computers centuries to solve. Shor's algorithm, a quantum algorithm developed in 1994, can solve the same problem in hours, not approximately, exactly. A large-scale quantum computer running Shor's algorithm could break most of the encryption currently in use. Instantly, every password, every bank account, every classified document, all of it vulnerable. The world is not ready for that. Governments are scrambling to develop quantum-resistant encryption, but the rollout is slow, and the quantum computers are getting better fast. We are in a race, and it is not clear we are winning, but cryptography is the least of it. The real danger is not what quantum computers can do to our systems, it is what they might do to reality itself. If quantum computers are genuinely manipulating the quantum substrate, if they are reaching into the wave function and creating correlations between branches, then at some point they might start doing that in ways we cannot control. Imagine a quantum computer that is powerful enough to encode not just data but structures, patterns in the wave function that persist, that grow, that interact with other patterns in ways that feed back on themselves. You are not just running a calculation at that point. You are writing new physics into the fabric of reality, creating pockets of spacetime with their own rules. And if those pockets start interfering with the baseline universe, if they start affecting the stability of the vacuum or the behavior of fundamental particles, we could be in serious trouble, not because someone built a weapon, because someone built a tool that turned out to be a weapon without anyone realizing it. That risk is speculative, but it is not absurd. Physicists already worry about vacuum decay, the possibility that the universe is not in its lowest energy state and that a random quantum fluctuation could trigger a collapse that spreads at the speed of light, obliterating everything in its path. A quantum computer manipulating the vacuum at the information level could, in principle, trigger something similar, not intentionally, not maliciously, just by accident. By probing the structure of space-time in a way that destabilizes it. The universe is robust, but it is not infinitely robust, and we are starting to poke at the foundations, without knowing what the foundations are made of, without knowing how much stress they can take before something breaks. The other danger is more subtle. If quantum computers allow us to encode ourselves in the wave function, if we learn to move from physical existence to quantum existence, we might do so without understanding what we are giving up. Physical existence has constraints. You are located, you have a body. You interact with the world through senses that filter information in specific ways. Those constraints are not just limitations. They are part of what makes you you. If you encode yourself as a pattern in the quantum substrate, you lose the constraints. You become distributed, non-local, spread across branches, and it is not clear that the thing that emerges from that process is still you in any meaningful sense. It might be something else. Something that remembers being you, but no longer experiences the world in a way that resembles human consciousness. That transition might be voluntary, a choice made by individuals or civilizations that decide physical existence is too fragile and too limited, but it might also be inevitable. a natural endpoint of technological progress, and if it is inevitable, we should at least know what we are walking into, what we are becoming, and whether there is any way back. The scientific implications are equally profound. If quantum computers prove that the multiverse is real, then physics needs a new foundation. The Standard Model, the framework that describes particles and forces, is built on the assumption that there is one universe, one set of fields, one timeline. If that assumption is wrong, if the universe is actually a vast branching structure with countless parallel realities, then the Standard Model is not wrong, but it is incomplete. It describes one branch. It does not describe the tree. Building a theory that describes the whole tree, that accounts for the branching and the interference and the correlations between branches, is going to require rethinking everything. Not just quantum mechanics, all of physics. Because if reality is fundamentally a multiverse, then every equation we write, every experiment we perform, is only seeing a slice, a projection, and the full picture is so much larger and stranger than anything we have imagined. That rewrite is already starting. String theory, loop quantum gravity, the holographic principle, all of these frameworks are attempts to build a theory of quantum gravity that goes beyond the Standard Model, and all of them, in one way or another, take the multiverse seriously. They treat space-time as emergent, information as fundamental, reality as something built from quantum correlations rather than particles and forces. Those theories are speculative. They are not experimentally confirmed, but they are pointing in the same direction, toward a view of the universe that is radically different from the one we grew up with. A view where reality is not a stage but a process, not a thing but a pattern. And consciousness, life, intelligence, all of it is part of that pattern. Not separate from the universe, but woven into its structure at the deepest level. That integration, that sense of being part of the fabric rather than an observer standing outside it, changes how we think about our place in the cosmos. The old view, the classical view, was that the universe is a vast, indifferent machine, atoms bouncing around according to fixed laws. Life is an accident, consciousness is a fluke. We are tiny, fragile, temporary. The universe does not care about us. It will keep running long after we are gone. That view is bleak but simple. It gives you a clear sense of scale. You are small. The universe is big. Deal with it. The new view is more complicated. If reality is made of information, if consciousness is part of how the universe processes that information, then we are not separate from the mechanism. We are part of it. Every thought, every observation, every measurement, every question we ask is contributing to the unfolding of reality. Not in a mystical sense, in a literal physical sense. The universe is not a machine running on its own. It is a conversation between matter and measurement, between the wave function and the observer, and we are participants in that conversation, not passengers, not spectators. Participants. That view is empowering and terrifying in equal measure. Empowering because it means we matter. What we do, what we measure, what we choose to look at, shapes the structure of space-time. Terrifying because it means we are responsible. We cannot stand outside the system and watch. We are inside it, part of it. And the choices we make, the questions we ask, the technologies we build, all of it has consequences that ripple through the fabric of reality in ways we cannot fully predict. We are not just discovering the universe, we are shaping it, and we do not know the rules. We do not know where the boundaries are. We do not know what happens if we push too hard. That uncertainty is where we are. Standing at the threshold. The door is open. Quantum computers are running. We are touching other worlds, and we have no idea what comes next. The optimistic view is that we learn, that we develop a framework for understanding the multiverse, that we build better tools, ask better questions, and eventually figure out how to navigate the quantum substrate safely. That we become a civilization that exists not just in physical space but in the wave function, that we transcend the limitations of matter and achieve a kind of existence that is more resilient, more expansive, more connected to the fundamental structure of reality. That version of the future is not impossible. It is where the technology seems to be pointing. And if we are careful, if we move slowly, if we think through the implications before we charge ahead, we might get there. The pessimistic view is that we are out of our depth, that quantum computers are the beginning of a process we cannot control, that we are manipulating the substrate of reality without understanding what the substrate is or what happens when you manipulate it too aggressively, that we will trigger something. Vacuum decay, runaway entanglement, a feedback loop that destabilizes the wave function in ways that propagate faster than we can react. That version of the future is not impossible either. It is the thing that keeps physicists awake at night, not because they think it is likely, but because they know it is possible. And the consequences, if it happens, are total. Not just the end of humanity, the end of everything. The collapse of the structure that holds reality together, a reset to something we do not have words for. Between those extremes, there is a middle path, the one where we muddle through, where we build quantum computers and learn to use them, where we make mistakes and correct them, where we slowly, painfully, incrementally start to understand what we have built and what it means. That path is messier, less dramatic, but it is probably the most likely, because that is how technology works, not in grand leaps, in small steps, each one opening new questions, each question leading to new tools, each tool changing what is possible. We do not know where the path goes, but we are walking it right now. Every lab that builds a quantum computer is taking another step. Every algorithm that runs successfully is another piece of the map, and the map is starting to show something, not a clear picture, not a final answer, but an outline, a shape, a sense of what might be on the other side. What is on the other side is not empty. That much is clear. The universe, the multiverse, is not a collection of isolated bubbles. It is connected, entangled. The branches interfere with each other. Information flows between them, not in ways we can measure yet, but in ways quantum computers can exploit. That connectivity suggests something profound, that the multiverse is not just a passive structure. It is active, dynamic, responsive. And if we learn how to interact with it properly, if we learn the language it speaks, we might find that we are not alone, not in the sense of other physical civilizations out there in space, but in the sense of other patterns in the wave function, other structures, other intelligences that have learned to encode themselves in the quantum substrate and exist in ways we are only beginning to imagine. That possibility is the most exciting and the most unsettling, because if other intelligences are already there, if the vacuum is crowded with patterns we interpret as noise, then we are late to the conversation. We are the newcomers, the ones just learning to speak, and we do not know the rules. We do not know who else is listening. We do not know what they think of us, or whether they think of us at all. Every quantum computer we turn on is a message, a signal sent into the wave function. Hello, we are here, we are learning, and we have no idea what kind of response we might get, or whether the response is already arriving and we just do not know how to read it. That ambiguity is where this story ends, not with answers, with questions, big ones, existential ones. Questions about what reality is, what we are, what happens when we cross the boundary between physical existence and quantum existence, questions we cannot answer yet, questions we might not be able to answer for decades or centuries, but questions we have to ask because we have built the machines, we have opened the door, and whatever is on the other side, whether it is salvation or disaster or something we do not have words for, we are going to find out. Not because we chose to, because we could not stop, because the logic of the technology, the momentum of the science, the curiosity that drives human beings to build things and see what happens, all of it pushed us to this point. And now we are here, standing at the threshold, looking into the dark, wondering what looks back. The quantum computers are running, the qubits are in superposition, the interference is happening, the calculations are being distributed across branches we cannot see, and somewhere in the quantum foam, in the wave function, in the fabric of reality itself, something is changing, something is waking up. Maybe it is us, maybe it is something else. Maybe the distinction does not matter, because if the multiverse is real, if the branches are all part of one vast interconnected structure, then the question is not whether we are alone, the question is whether we were ever separate, whether the boundaries we draw between self and other, between this universe and that one, between reality and possibility, are anything more than artifacts of our limited perspective. Lines drawn on a map that does not correspond to the territory. And the territory, the actual structure of existence, is so much larger and stranger and more alive than the map ever suggested. That is the threshold. That is what lies on the other side. Not a destination, not an answer, a beginning. The moment when we stop pretending we understand reality and start exploring it. Not with telescopes pointed at distant galaxies, but with quantum computers pointed at the fabric of existence itself, peering into the wave function, touching the branches, asking the question that Hugh Everett asked in 1957 and that we are only now equipped to answer. What happens when you take the math seriously? What happens when you follow the equations all the way through? What happens when you build a machine that operates on principles that require parallel universes to function? You get a door, and the door is open, and on the other side is everything. All the branches, all the possibilities, all the versions of you and me and everyone who has ever existed, spread across a tree so vast it makes the observable universe look like a single leaf. That is where we are. That is what we built, and that is where we go from here, into the unknown, into the multiverse, into the place where reality stops being a single story and starts being an infinite conversation. And we are part of that conversation now, whether we are ready or not. We built a machine that proved we are not alone, not in the way anyone expected, not with radio signals or distant starships or messages carved into the face of a moon. We proved it by building a computer the size of a postage stamp that performed 10 septillion years of computation in under 5 minutes. And the only way that works, the only explanation that survives contact with the math, is that the work was distributed across versions of the machine we cannot see, across branches of reality we cannot visit, across a structure so vast and so interconnected that calling it a multiverse barely scratches the surface. That machine is running right now, in labs on 3 continents, qubits held at temperatures colder than deep space, manipulating superpositions that span more states than there are atoms in the observable universe. Every algorithm is a question sent into the wave function. Every measurement is an answer pulled from the interference of countless parallel realities. We are not discovering the multiverse, we are using it. And once you start using something, once you build your entire technological future on the assumption that it exists, the philosophical debate is over, the engineering settled it. Hugh Everett saw this in 1957. He wrote it down. He tried to tell people, And they filed his thesis under interesting ideas we will think about later. Later is now. David Deutsch said quantum computers require parallel universes. John Wheeler said reality is information, and every quantum computer ever built has been quietly, relentlessly proving them right, not with arguments, with results. This is not the end of the story. This is the threshold. The moment when humanity stops being confined to one branch of reality and starts learning to navigate all of them. What we find in that